Level 1. The illusion of time. It flows steadily, relentlessly, from past to present to future. Or so we believe. Yet, when you truly pause and examine it, time becomes a profound mystery. Is time an objective reality that ticks away independent of our awareness? Or is it merely an illusion created by our minds? Consider how we experience time. As we age, minutes seem to pass quicker, while during moments of intense emotion or boredom, a single minute can stretch into what feels like an eternity. Such variations beg the question, does time really exist in a fixed, measurable way, or is it subjective, woven from the fabric of our perception? Modern physics, especially Einstein's theory of relativity, has already shattered the notion of time as an absolute constant. Time can slow down or speed up depending on your speed and the gravitational field you're in. Astronauts, for instance, age slightly slower in orbit compared to those on Earth. In these cases, time appears to be more malleable than we ever imagined. Some scientists even speculate that, at the most fundamental level, time might not exist at all, merely an emergent property of a deeper reality that our minds have constructed to make sense of events. In the quantum realm, particles exist in states that defy classical timekeeping, existing in superpositions where the concept of a clear beginning and end becomes blurred. Every moment, every memory, and every expectation is filtered through the lens of our consciousness, making the passage of time appear to fluctuate. What if the flow of time is not an inherent feature of the universe, but rather a byproduct of how we process change? When you remember your childhood, the moments feel long and detailed. Yet, when you recall recent events, they seem fleeting. This discrepancy may hint that time, as experienced by humans, is a cognitive construct, an elaborate illusion that organizes our lives. If time is indeed an illusion, then perhaps everything we consider as history, the present and the future, is already fixed, existing in a vast, timeless tapestry. Our linear experience of time might simply be the way our minds traverse this tapestry, moving along a path that feels like time's arrow. The illusion of time challenges us to rethink not only how we measure seconds and minutes, but also how we perceive existence itself, urging us to question whether the relentless ticking of a clock truly represents reality, or if it's merely a comforting construct to which we cling. Level 2. The infinite position. Imagine an object, a small ball, perhaps seemingly fixed in place on a table. In our everyday world, we assume it occupies a single precise position. But what if, at the most fundamental level, that object exists not at one point, but as a probability spread across space? In the strange realm of quantum mechanics, particles do not have definite positions until measured. Instead, they are described by a wave function that gives a probability distribution of where they might be. This concept, known as superposition, means that before you observe the ball, it doesn't sit neatly in one spot. Rather, it exists in multiple positions at once. Only when you look does the ball choose a location, collapsing from a blur of possibilities into a single point. But does this single point truly represent where the object is? Or is it merely a convenient illusion crafted by our active observation? The infinite position paradox invites us to consider whether objects are inherently localized. Our classical intuition tells us that every object has a fixed, static location, yet quantum physics suggests a far more mysterious reality. Before measurement, the object is spread out, a shimmering probability cloud that defies the familiar notion of position. It challenges the idea that the world is built from tiny, discrete points. Instead, it hints that the fabric of reality is a continuum, where boundaries are fuzzy and positions are infinite possibilities waiting to be narrowed by our perception. If an object can be in many places at once, what does that say about the nature of existence itself? Perhaps every moment, every location is not singular, but a blend of endless potential positions. The act of observation then becomes a powerful force that chooses reality from a canvas of infinite possibilities. This may imply that our Perception of stability is not an inherent trait of objects, but a result of the human mind forcing order on a fundamentally indeterminate world. Such a perspective turns our understanding of space on its head. We might ask, if everything exists in a state of infinite position until observed, then are our lives merely a series of decisions that fix our location in the vast probabilistic cosmos? The infinite position paradox urges us to question the solidity of the world around us, revealing a universe where everything is in constant flux until we decide to see it otherwise. Level 3. The unmeasurable distance, a simple concept in everyday life, measured in feet, meters, or miles, suddenly transforms into an enigma when we delve into the quantum realm. What if, at the smallest scales, measuring distance becomes an impossible task? In our macroscopic world, the space between objects seems clearly defined, but in the quantum world, particles are governed by uncertainty. According to Heisenberg's uncertainty principle, you cannot simultaneously know a particle's exact position and momentum. As a result, at the quantum level, the notion of a precise distance dissolves into a probabilistic haze. Two particles may be linked by interactions that seem to occur over an undefined span, where distance is not a fixed parameter but an ever-changing uncertainty. Imagine trying to measure the space between two electrons. They are so small and so fuzzy that traditional measurements break down, leaving only probabilities and possibilities. The unmeasurable distance paradox challenges our intuitive understanding of space. If the fabric of reality is composed of probabilities, then distance itself may be more a measure of our perception than an inherent quality of the universe. Our instruments are designed to measure macroscopic distances with precision, but they falter when faced with the quantum realm, where everything is in a state of flux. In such a realm, objects do not have clearly defined edges, and the space between them is more like a fog than a vacuum. Furthermore, consider the vast cosmic scales where gravitational waves and the curvature of space-time come into play. In these realms, distance is distorted by gravity and time. The distance between two stars might not be a constant value. It may stretch and compress as space itself warps under the influence of massive objects. Thus, the concept of unmeasurable distance suggests that what we take for granted as the clear separation between objects might be nothing more than a useful approximation for our limited macroscopic perception. In truth, the universe may be a seamless, continuous field where distance is not fixed but exists as a fluid and dynamic entity, measurable only in theory, but elusive in practice. This paradox invites us to rethink how we define space and challenges our understanding of the very architecture of the cosmos. Level 4. The mass that changes mass is something we assume to be constant. When you hold a rock, you expect its weight to remain the same, whether it's on Earth or in deep space. But what if mass isn't a fixed property? What if it shifts and changes not just due to external forces, but because of something deeper, something unseen? In Einstein's theory of relativity, mass isn't absolute. It depends on speed. As an object moves faster, its mass increases. If you were traveling at 90% of the speed of light, your mass would nearly double. At 99.99% the speed of light, your mass would become almost infinite. But why does this happen? The answer isn't simple. Some physicists argue that mass itself is a consequence of energy, meaning it's not an inherent property, but a dynamic one, shaped by motion and interaction. Now consider quantum physics, where particles behave in unpredictable ways. The Higgs field, an invisible energy field filling the universe, is believed to be the reason particles have mass at all. If the Higgs field fluctuates or behaves differently in some parts of the universe, could mass itself be unstable? Could there be regions in space where objects weigh nothing at all? Or worse, what if mass could vanish altogether? The implications are profound. If mass isn't constant, then reality isn't as solid as we think. If mass can be altered, manipulated, or even erased under the right conditions, what does that say about our existence? Are we as fixed in reality as we assume, or are we just temporary formations of mass, fluctuating like shadows in the cosmic wind. Level 5. The dance of motion. Everything moves. Even when you think you're perfectly still, you're not. The Earth is rotating at 1,000 miles per hour, orbiting the Sun at 67,000 miles per hour, and hurtling through the galaxy at over 500,000 miles per hour. And yet right now, you feel like you're sitting still. Why? Motion is relative. If you're inside a spaceship traveling at a constant speed, you feel motionless. You could toss a ball, and it would behave exactly as if you were standing on Earth. But the moment acceleration occurs, everything changes. This is because motion only matters when compared to something else. It's not an absolute state, but a relationship between objects. Now imagine this. What if motion never truly stops? Quantum mechanics suggests that even at absolute zero, when all thermal movement should cease, particles still vibrate due to quantum fluctuations. This means that true stillness is impossible. Even at the smallest levels of reality, motion continues in some form, as if the universe itself is never at rest. Could this mean that what we perceive as motion is just one layer of a deeper dance? Could it be that movement is not just physical, but woven into the very essence of existence? If so, does this mean everything, every thought, every event, every possibility is constantly in motion, even if we don't see it? Level 6. The secret of speed is something we think we understand. A car moves at 60 mph, a plane at 500 mph, light at 186,000 miles per second. But what if there's something faster than light? What if there's something that moves instantly? In classical physics, nothing can exceed the speed of light. It's a fundamental limit, a cosmic speed barrier. But in the quantum world, strange things happen. Quantum entanglement allows two particles to be linked, no matter how far apart they are. When one changes, the other reacts instantly, even if they're light years away. This suggests that information can travel faster than light, or perhaps even outside time itself. But what if speed itself is an illusion? Einstein's theory of relativity suggests that time slows down as you approach the speed of light. If you could reach light speed, time would stop entirely. And if you went faster, time might reverse or cease to exist in the way we understand it. Some theories even suggest that tachyons, hypothetical particles, might already exist beyond light speed, meaning they don't travel through time the way we do. Now imagine this. What if there is something beyond motion itself? A state where movement and stillness merge, where speed is irrelevant because everything happens at once? Could the ultimate secret of speed be that speed, as we know it, is just a construct of our limited perception? If something can truly move instantaneously, then what does that mean for space, time, and the nature of reality itself? Level 7. The phantom velocity. Velocity is normally defined as the rate at which an object moves in a given direction, a measurable quantity that we experience daily. But what if an object could reach an infinite speed, moving so fast that it transcends our conventional understanding of space and time? Imagine a particle that doesn't just travel at high speed, but does so instantaneously, arriving at its destination in a flash of existence. In classical physics, nothing can exceed the speed of light. Yet theoretical constructs such as tachyons hint at possibilities beyond our standard model. These hypothetical particles, if they exist, could travel faster than light, challenging the cause and effect order and defying our intuitive grasp on motion. Consider the concept of phantom velocity as a state where velocity is no longer limited by traditional boundaries. In this state, distance becomes irrelevant because the moment of departure is identical to the moment of arrival. This idea shakes the very foundation of our understanding of movement. If an object's speed were infinite, then the separation between 2 points would vanish, and our everyday measures of space would collapse into nothingness. In a universe where phantom velocity is possible, even the concept of delay or travel time would be obsolete, leaving us with a reality where everything is connected instantaneously. This paradox invites us to question whether our familiar laws of motion are complete. Is velocity an intrinsic property of objects, or is it a construct emerging from our limited perception of time and space? If objects could exhibit infinite speed, then they would be everywhere at once, a surreal state that mirrors some interpretations of quantum mechanics, where particles exist as probability clouds until measured. Could our macroscopic world be just a shadow of these deeper, untethered phenomena? Ultimately, the phantom velocity paradox challenges our deepest notions of movement and connectivity. It forces us to ask, what is the nature of motion if the usual constraints of speed and distance dissolve? And if infinite velocity is possible, what does that imply about the structure of reality itself? The idea may seem far-fetched, yet it opens the door to a universe where the boundaries between here and there, now and then, vanish in an instant, leaving us with an awe-inspiring glimpse of a realm beyond our current understanding. Level 8. The shadow of acceleration. Acceleration is defined as the change in velocity over time, a forceful push that causes objects to speed up or slow down. But what if acceleration could exist independently, like a shadow that follows without being tied to a direct force? Imagine an object that begins to accelerate without any apparent push or pull, a phenomenon that defies Newton's second law, which states that force equals mass times acceleration. In our everyday experiences, acceleration always requires a force, be it gravity, a motor, or a hand pushing an object. Yet the concept of a shadow of acceleration implies that there might be instances where acceleration manifests on its own, as if emerging from the fabric of space itself. In the realms of cosmology and quantum physics, unusual forms of acceleration are not unheard of. The expansion of the universe is accelerating, driven by a mysterious dark energy that we have yet to fully understand. Could dark energy be a manifestation of acceleration that exists independently of a conventional force? Similarly, at the quantum level, particles sometimes exhibit sudden changes in velocity that seem to occur without any clear external impetus. Such observations force us to reconsider the fundamental relationship between force and motion. If acceleration can occur without a corresponding force, then our understanding of dynamics might be incomplete. It suggests that space-time itself might harbor intrinsic accelerative properties, an underlying current that propels objects without a visible cause. This raises profound questions. Is the acceleration we experience in our daily lives simply a localized phenomenon, while the true nature of acceleration is woven into the cosmos at large? And if so, could harnessing this shadow of acceleration lead to breakthroughs in propulsion or energy? The shadow of acceleration paradox challenges the boundaries of classical mechanics. It asks us to reimagine a universe where motion can emerge from the void, where the change in speed is a natural, spontaneous occurrence, not merely the result of applied forces. As you drift into sleep, let your mind wander through this concept and consider that perhaps the very act of moving is more mysterious than it appears. Level 9. The force beyond physics. Every event, every movement in the universe is driven by forces, gravity, electromagnetism, and the nuclear forces that bind atoms together. Yet, what if there exists a force so elusive, so profound, that it lies beyond the boundaries of our current understanding of physics? Imagine an unseen power that shapes the formation of galaxies, influences the flow of time, and subtly guides the evolution of the cosmos. This is the force beyond physics paradox, a challenge to our belief that we know all the fundamental forces governing existence. Our modern understanding is built on 4 fundamental forces. However, anomalies such as dark matter and dark energy suggest that there might be additional influences at work. Dark matter, for example, is invisible yet exerts a gravitational pull that holds galaxies together. Dark energy accelerates the universe's expansion. But what if these mysterious phenomena are manifestations of an entirely new force, one that orchestrates the grand cosmic dance in ways we have yet to detect? Consider that this unknown force could be responsible for phenomena that seem to defy logic. It might explain why certain particles behave unpredictably or why the universe appears finely tuned to support life. Perhaps it even governs the delicate balance between order and chaos at the quantum level, stitching together the fabric of reality in ways our instruments cannot measure. If such a force exists, it would not only expand our understanding of physics, but also redefine the nature of reality itself. It might be the missing link between quantum mechanics and general relativity, a unifying power that brings harmony to the discord between the very small and the very large. In this light, the force beyond physics becomes more than just a hypothetical idea. It represents the next frontier of scientific discovery, one that could reshape everything from how we harness energy to how we perceive our place in the cosmos. As you let these ideas sink in, consider the possibility that the universe still holds secrets that defy explanation, a force waiting to be discovered that will challenge and expand the boundaries of human knowledge. Could it be that this unknown force is the true architect of the cosmos, operating silently, shaping everything, from the birth of stars to the unfolding of life itself? Level 10. The hidden inertia in everyday life. Inertia is the tendency of an object to resist changes in its state of motion. We know from Newton's first law that an object at rest stays at rest, and one in motion remains so unless acted upon by an external force. But what if inertia isn't solely a property of mass? Imagine an object that seems to resist motion even when its mass is negligible or, theoretically, non-existent. Could there be a hidden inertia, a kind of ghost resistance that persists independent of mass? Modern physics tells us that mass and energy are interchangeable, and that mass might even be an emergent property resulting from interactions with fields like the Higgs field. In this light, inertia could also be more than a mere byproduct of mass. Perhaps it is a fundamental characteristic of matter, or even space-time itself, that ensures stability. Think of inertia as an unseen tether, a force that holds the fabric of motion together even when the object in question has little or no mass. Consider the behavior of light. Photons are massless particles, yet they always travel at a constant speed in a vacuum. They don't accelerate or decelerate in the usual sense, suggesting that even massless entities follow certain rules of motion dictated by the underlying structure of space and time. Could this be a clue that inertia, as a concept, extends beyond mass? What if the resistance to change in motion is built into the very geometry of the universe, providing a form of hidden inertia that applies to all things, massive or massless? This paradox challenges our intuitive understanding of movement. If inertia exists independent of mass, then the apparent resistance of objects to change must have a deeper, more fundamental origin. It invites us to consider that what we call inertia might be a property of the vacuum, an intrinsic quality of the cosmos that ensures objects maintain their state unless a force, possibly even a subtle one we have yet to detect, intervenes. As you contemplate this idea, let your mind wander to a universe where motion is not just a consequence of mass, but a dynamic interplay between energy, space, and unseen forces. What if the stability you feel in the world is not merely because objects are heavy, but because the very fabric of reality resists change? In that case, inertia becomes not just a principle of physics, but a guardian of cosmic order, a hidden law that keeps the universe in balance, even when nothing seems to be there to enforce it. Level 11. The momentum. Mystery. Momentum, defined as the product of mass and velocity, is one of the cornerstones of physics, a conserved quantity that remains constant in a closed system. But what if momentum could be lost, or even transferred, in ways that defy our understanding? Imagine a scenario where an object's momentum dissipates without any external force acting upon it, vanishing into thin air as if it were never there. This is the momentum mystery, a paradox that challenges the fundamental law of conservation of momentum. In classical mechanics, momentum conservation is sacrosanct. When you throw a ball, your hand imparts momentum that the ball carries through. space until friction or another force gradually slows it down. But in the quantum realm, the rules can become fuzzy. Particles behave unpredictably, and sometimes what seems like a loss of momentum may be a hidden exchange with the surrounding quantum field. Yet some experimental results hint at events where momentum appears to vanish, even as the system remains isolated. If momentum truly can be lost, then we must ask, where does it go? Is it transferred to an unknown field, or does it dissipate into a form of energy that we have yet to recognize? Perhaps momentum isn't a static quantity but a dynamic one that can morph into other forms under specific conditions. This challenges the notion that the universe is perfectly balanced in terms of movement. It suggests that our understanding of conservation laws may be incomplete, with hidden processes at work beneath the surface. Now, consider the implications on a cosmic scale. Galaxies, stars, and planets all move with tremendous momentum. If even a small fraction of that momentum could vanish mysteriously, the structure of the universe itself might change over time. Could this phenomenon contribute to the gradual evolution of cosmic systems, altering orbits and trajectories without any visible cause? The momentum mystery encourages us to look deeper into the unseen interactions of matter and energy. It invites the possibility that what we perceive as a loss might be a transformation, a conversion of momentum into a form of energy that quietly sustains the universe's hidden dynamics. As you drift into a state of calm, let your thoughts ponder this mystery. Is the momentum you observe truly eternal, or is it part of a larger, more mysterious dance of energy and matter that we are only beginning to understand? Level 12. The impulse. Illusion. Impulse is defined as the change in momentum, resulting from a force acting over a period of time. In our daily experiences, every impact, every sudden movement is accompanied by a discernible impulse, a brief, intense surge of energy that propels objects into motion. But what if impulses could occur even before we detect any force at all? What if the universe is capable of initiating change in ways that appear to defy causality? This is the impulse illusion, a paradox that challenges our understanding of cause and effect. Imagine that you reach out to catch a ball. In a normal scenario, your hand moves in response to the force of the ball's impact. But now, envision a scenario where the ball seems to alter its course before your hand even reacts, as if an unseen impulse already set it on a new trajectory. In this strange world, the force appears to act before any interaction is noticed, a premonition of motion. Quantum mechanics already teaches us that the behavior of particles can be unpredictable and that outcomes can remain uncertain until measured. Could the concept of impulse also be subject to quantum uncertainty? Some theoretical models suggest that forces might be initiated by fluctuations in the quantum field, causing an impulse to occur before it is consciously recognized. In this way, the impulse illusion challenges the conventional sequence of events: cause, then effect. If an impulse can happen before detection, what does it mean for our concept of free will and control? Are our actions preemptively set in motion by unseen energies that our minds can barely comprehend? Imagine the possibility that every sudden movement or reaction in your life is actually triggered by an impulse you never consciously perceived, leaving you to wonder if your choices are really your own. The impulse illusion forces us to question whether every action we observe follows a clear, linear path from cause to effect, or if there exists a hidden layer where forces act in advance, setting the stage for the events we later perceive. As you let this idea sink in, consider that what you think of as instantaneous might actually be a carefully orchestrated moment, one where the universe hints at a deeper, more enigmatic order that lies just beneath the surface of reality. Level 13. The hidden laws of motion. Newton's laws of motion are the foundation of classical physics. They describe how objects move, how forces interact, and how the universe follows predictable rules. But what if these laws aren't as absolute as we think? What if, under extreme conditions, they begin to break down, revealing hidden forces that exist beyond our understanding? At everyday scales, Newton's laws work perfectly. They explain why a car stops when brakes are applied and why a thrown ball follows a predictable arc. But as we move to the edges of the universe, into the realm of black holes, quantum particles, and near light speeds, something strange happens. The rules we take for granted begin to warp, twist, and in some cases vanish completely. For instance, Newton's first law states that an object in motion stays in motion unless acted upon by an external force. But in the quantum world, particles can appear and disappear, existing in multiple states at once. They are not bound by classical inertia. Could it be that Newton's laws only apply to a narrow slice of reality? That in the vast hidden structure of the universe, motion follows different rules we have yet to discover? Even Newton's third law, every action has an equal and opposite reaction, starts to blur in extreme scenarios. In the depths of space, where gravitational forces bend light and time itself, action and reaction may not be perfectly balanced. Could there be hidden forces at play, causing energy and motion to act unpredictably? Some physicists speculate that dark matter and dark energy, mysterious substances that make up most of the universe, could be influencing motion in ways we cannot yet measure. If Newton's laws are not universal, then what governs the universe at the most fundamental level? Are there deeper laws waiting to be uncovered? Or do we only see a fraction of the true nature of motion? Perhaps reality itself is shifting, evolving, and revealing only as much as we are ready to understand. As you relax, let your mind drift into a world where motion is not as simple as we once thought. A world where objects move in ways we cannot yet predict, where forces exist beyond our detection, and where the very laws we rely on may one day be rewritten. Level 14. The gravity. Anomaly gravity. The force that keeps us grounded, that binds planets in orbit, that holds galaxies together. It is the invisible hand shaping the universe. But what if gravity isn't a force at all? What if it is merely an illusion, an effect of curved space rather than a fundamental interaction? For centuries, scientists believed gravity was an actual, pulling force, much like a magnet attracting objects. But Einstein's theory of general relativity changed everything. He proposed that gravity isn't a force at all. It's a bending of space-time caused by massive objects. The Earth orbits the Sun not because it is being pulled, but because the Sun creates a dip in space-time, and Earth simply follows that curve. This idea raises a fascinating question. If gravity is just curved space, could it ever be manipulated, weakened, or even turned off? Some physicists speculate that if we could control gravity, we could manipulate space-time itself, leading to the possibility of anti-gravity technology or even faster-than-light travel. But here's where the gravity anomaly deepens. At the quantum level, gravity doesn't behave the way it should. Unlike the other fundamental forces, electromagnetism, the strong force, and the weak force, gravity does not fit neatly into quantum mechanics. In fact, we have never successfully observed a gravity particle, or graviton, even though other forces have their own carrier particles. This suggests that gravity operates on a completely different level than anything else in physics. What if gravity, as we understand it, is only a shadow of a much deeper, more complex phenomenon? Some theories suggest that gravity might not even originate from within our universe, but is instead a projection from higher dimensions. Could it be that what we experience as a force is merely the side effect of interactions happening beyond our perception? As you drift deeper into thought, consider the possibility that gravity isn't as simple as we've been taught. What if it could one day be controlled, reversed, or even bypassed? If gravity is not a force, but a distortion of space, then perhaps reality itself can be shaped, altered, and redefined. Level 15. The fall that never ends. Imagine dropping an object and watching it fall. Forever. A motion that never stops, never slows, never reaches a final destination. Is such a thing possible? Could an object exist in a state of endless free fall? On Earth, falling objects eventually reach the ground. their journey cut short by the surface beneath them. But in space, things are different. Astronauts aboard the International Space Station experience free fall continuously, not because they are floating, but because they are falling around Earth at just the right speed. They never touch the ground because the planet curves away beneath them. Now, take this concept to an extreme. If an object could exist in perfect balance between gravitational forces, caught between stars, galaxies, or even black holes, it could, in theory, fall forever, never reaching a final rest. Some believe this might even explain the strange orbits of celestial bodies that defy our understanding. But let's go further. What if an object could fall not just through space, but through time? If space and time are linked, as Einstein suggested, then free fall could extend beyond the physical into the temporal. Some physicists speculate that black holes may contain regions where time itself flows differently. If an object were to fall into such a place, could it fall not just through space but into the future, or even into another universe entirely? Even here on Earth, experiments with superconductors and magnetic fields have shown that objects can enter states of seemingly perpetual motion, suspended in ways that defy gravity. Could it be that free fall is not just a simple downward motion, but a gateway into understanding how forces interact at a much deeper level? As you listen, let yourself drift into this endless fall, where motion never stops, where space and time stretch infinitely. If free fall can continue forever, then perhaps movement itself is a deeper mystery than we ever imagined, one that might one day unlock the true secrets of the universe. 18. The friction paradox. Friction is the force that slows everything down, whether it's the brakes on a car, the resistance you feel when sliding your hand over a surface, or even the friction between molecules that creates heat. In our everyday world, friction seems to be the great equalizer, gradually bringing all motion to a halt. Yet, when we gaze into the cosmos, we see galaxies spinning, stars orbiting, and planets hurtling through space at incredible speeds. If friction always slows motion, why does the universe keep moving? The answer lies partly in the nature of friction itself. On Earth, friction is a result of the interaction between surfaces and the atmosphere. In the vacuum of space, where there is little to no matter to create resistance, objects can maintain their momentum for billions of years. But even beyond this obvious explanation, the friction paradox challenges our deeper understanding of motion. What if friction isn't merely a force that opposes movement, but also a fundamental property that plays a role in balancing the dynamics of the cosmos? Consider how friction influences energy transfer. When friction is present, kinetic energy is transformed into heat, a process that seems wasteful in a closed system. Yet the universe doesn't waste all its energy through friction. It appears to recycle and redistribute energy in ways that defy simple decay. The friction we experience on Earth is a localized phenomenon. Its effects are intense in dense, matter-rich environments, but become negligible in the vast emptiness of space. In addition, on cosmic scales, gravitational forces and dark energy work in concert to propel and sustain motion, effectively counterbalancing any minute frictional losses that might occur in sparse interstellar mediums. This paradox forces us to rethink the nature of energy conservation. While friction slows objects in our everyday experiences, the universe as a whole seems to operate under a different set of principles, where motion and energy persist in a grand, self-sustaining cycle. The friction we see is just one aspect of a much larger dynamic interplay of forces that keep the cosmos alive and moving. As you drift into a relaxed state, consider the elegance of a universe where, despite the constant pull of friction on a small scale, vast systems continue to dance through space. It's a reminder that the laws governing our daily experiences might only be a part of a far more intricate tapestry of cosmic motion, a tapestry where friction, though ever present, is balanced by forces that maintain the perpetual rhythm of the universe. Level 17. The invisible air. Resistance. Air resistance is the gentle pushback we feel when moving through the atmosphere. A subtle force that slows down a speeding car, or makes it harder to run against a strong wind. It's not as obvious as friction on a solid surface, yet its presence is undeniable in our daily lives. But have you ever stopped to wonder, does air push back even when we don't feel it? And more importantly, what happens when this invisible force is removed or altered? In our world, air is omnipresent. We breathe it, and it surrounds every object, exerting a constant, though often imperceptible force. When you cycle, you feel the wind's resistance. When a paper airplane glides, it is continually buffeted by tiny currents of air. Even in moments of calm, air molecules collide with your skin at tremendous speeds, though you are unaware of this invisible dance. The phenomenon, known as air resistance, not only slows objects down, but also influences their shape, stability, and trajectory. But consider a scenario where air resistance is altered, either diminished or amplified. In the vacuum of space, where air resistance is virtually non-existent, objects can travel indefinitely without slowing. This contrast makes us question the role that air plays in the behavior of matter. Does air always push back in the same way? Or could there be situations where its effect is so subtle that it is almost an illusion? Recent experiments in aerodynamics have shown that at high altitudes, where the air is thinner, resistance is drastically reduced, affecting everything from the flight of birds to the performance of high-speed aircraft. Even on Earth, microscale studies reveal that air resistance behaves unpredictably when interacting with surfaces at the molecular level. This leads us to wonder whether air, though invisible, is a dynamic and variable force, one that might change based on environmental conditions, the nature of the surface it encounters, or even quantum fluctuations. As you settle into relaxation, imagine a world where every breath, every movement, is subtly influenced by an ever-changing air resistance, a force that, while unseen, is continuously shaping your experience of motion and stillness. The invisible air resistance paradox reminds us that even the simplest, most familiar forces hide layers of complexity that challenge our understanding of nature. Level 18. The work of the unknown. Work, in the physical sense, is defined as force applied over a distance, a clear, measurable process. Yet, imagine if work could be done without an apparent force, if energy could be transferred in ways that defy our conventional understanding. This is the work of the unknown paradox, a mind-bending idea that challenges the very concept of cause and effect in the universe. Typically, when you push a box across the floor, you apply force over a distance and the box moves. The energy you expend is measurable, predictable, and follows the well-established laws of physics. But what if, in some mysterious circumstance, an object moves or changes state without any observable force acting upon it? Could there be a hidden mechanism by which work is performed, one that bypasses the traditional transfer of energy? In the realm of quantum mechanics, particles behave in ways that are deeply counterintuitive. They can tunnel through barriers without any classical force, appearing on the other side as if they had done work to overcome an obstacle. This quantum tunneling suggests that, at a fundamental level, there might be forms of work that we do not yet understand, where energy is transferred in discrete, almost magical leaps rather than smooth, continuous flows. Moreover, dark energy, the mysterious force driving the accelerating expansion of the universe, appears to do work on cosmic scales, pushing galaxies apart despite the absence of a clearly defined force in the traditional sense. Could dark energy be a manifestation of the work of the unknown, an unseen process that quietly reshapes the cosmos? Consider also the phenomenon of superconductivity, where electrons flow with zero resistance. In such cases, work is done, but the usual energy loss associated with friction or heat is absent. This defies our classical understanding and suggests that there may be alternative pathways for energy transfer, where work occurs without the conventional markers of force. As you relax and allow your mind to wander, think about a world where energy moves in secret channels, where work is done by forces that remain hidden from our everyday perception. The work of the unknown. paradox challenges us to expand our understanding of energy, prompting us to consider that there might be unseen forces and processes at work, continuously shaping the universe in ways we have yet to discover. Level 19. The energy that never dies. Energy is famously conserved. It can neither be created nor destroyed, but this raises an intriguing question. Where does it truly go? In every action, every movement, energy is transformed from one form to another. When you turn on a light, electrical energy transforms into light and heat. When you run, chemical energy in your muscles converts into kinetic energy and a bit of heat. Yet, despite all these transformations, the total energy remains constant. This conservation law is one of the cornerstones of physics. But what if, beneath this fundamental principle lies a deeper mystery? A secret reservoir of energy that never dies, persisting through every transformation and hiding in the subtle folds of the universe. Imagine the energy in a star. It burns fiercely for millions of years, converting hydrogen into helium in its core, releasing enormous amounts of light and heat. Yet, even after the star dies, its energy does not vanish. It spreads out into space, contributing to cosmic background radiation and seeding the formation of new stars and planets. Energy's eternal nature means that every photon of light, every electron's movement, and every spark of heat is part of an endless cycle, constantly recycling through the cosmos. The energy that never dies paradox challenges us to consider, if energy is always conserved, could there be hidden, unaccounted for forms of energy at work, mysterious currents flowing through the fabric of space-time, waiting to be discovered? Furthermore, at the quantum level, particles engage in a ceaseless dance where energy fluctuates in seemingly impossible ways, as seen in virtual particles that pop in and out of existence. Although these fluctuations are transient, they contribute to a vibrant dynamic background that permeates the universe. This mysterious energy might be the underlying essence that fuels everything from the tiniest atoms to the grandest galaxies. As you drift into a state of calm, ponder this. Every action, every movement, every burst of light is an echo of energy that never truly dies. It transforms, it shifts, yet it is eternal, a hidden lifeblood that courses through the cosmos, binding every particle and phenomenon in a continuous, unending cycle. Level 20. The two faces of energy presents itself in seemingly opposite forms: kinetic energy, the energy of motion, and potential energy, the stored energy of position. At first glance, these appear as distinct, opposing concepts. Kinetic energy is dynamic, actively propelling objects through space, while potential energy is latent, waiting to be released. Yet they are two sides of the same coin, a seamless interplay that governs every process in the universe. When you roll a ball down a hill, its potential energy, derived from its elevated position, converts into kinetic energy as it gains speed. The sum of these energies remains constant, illustrating the principle of conservation. This elegant balance between the two forms is a cornerstone of classical mechanics. However, the paradox arises when we ponder their true nature. Are these energies fundamentally different, or are they simply different expressions of a single underlying phenomenon? In the realm of quantum mechanics and relativity, the distinction between kinetic and potential energy blurs. Particles can exist in states where energy is both stored and in motion simultaneously, defying our classical intuition. The transformation between these forms is so smooth that it seems almost magical. Energy continuously morphs from potential to kinetic, and back again, like a never-ending dance. Consider a compressed spring. It holds potential energy until released, at which point it transforms into kinetic energy as it propels objects outward. Yet even as the energy converts, some of it remains stored in vibrations or heat, hinting at an intricate balance that we only partially understand. Reflect on this paradox as you drift off. The two faces of energy are not separate entities, but parts of a unified whole. They illustrate that what we see as motion and rest, activity and stillness, are just different states of the same eternal force, a constant, fluid interplay that underpins every facet of the cosmos. Level 21. The power. Paradox power is defined as the rate at which work is done or energy is transferred. In everyday life, we experience power when a car accelerates or a light bulb illuminates a room. But what if power could exist without motion, if energy could be expended without any observable change? This is the power paradox, an idea that challenges our intuitive understanding of energy and work. Typically, we believe that to generate power, there must be movement, a force causing acceleration or transformation. For example, when you push a door open, you do work, and power is the measure of how quickly that work is done. Yet consider the notion of potential energy stored in a battery. Even when it sits motionless on a table, that battery holds power. Energy, ready to be unleashed at a moment's notice. But what if there is a form of power that exists independent of motion? Some theories in modern physics hint that energy may be stored in the very structure of space-time. This hidden power might not be apparent through conventional means because it does not result in immediate movement. Instead, it could be the force that underlies the creation of energy itself, a latent, ever-present potential waiting for the right moment to manifest. This paradox pushes us to question the very definition of work and energy transfer. If power can exist in a dormant state, then perhaps our conventional measurements are missing a layer of reality, a subtle energy that fuels the cosmos without leaving a trace of motion. Consider the vast emptiness of space, where dark energy is thought to drive the expansion of the universe. Though unseen and intangible, this force represents power at its most mysterious, influencing the fate of galaxies without a single moving part visible to the naked eye. As you relax and let your mind wander, reflect on the possibility that the power you rely on every day may be just the tip of an immense hidden iceberg of energy, one that operates in silence and stillness, yet is capable of transforming the universe itself. The power paradox invites you to envision a reality where movement and energy are not always visible, but where the potential for action is eternal, waiting to be awakened. Level 22. The law that never breaks. The conservation of energy is one of the most revered laws in physics, an axiom so foundational that it is often taken as the bedrock of our understanding of the universe. We are taught that energy can neither be created nor destroyed. It only transforms from one form to another. But what if this law isn't as absolute as we assume? What if there exists a hidden realm where energy, while seemingly conserved in our observable universe, is actually exchanged with forces or dimensions beyond our grasp? In our everyday experiences, when you drop a ball or turn on a light, energy shifts forms. Potential energy becomes kinetic energy, or electrical energy converts to light and heat. This seamless conversion forms the basis of everything from engine efficiency to the functioning of our own bodies. Yet, deep in the theoretical realms of modern physics, some questions arise. Could there be scenarios where energy appears to vanish, only to re-emerge elsewhere, undetected by our instruments? For example, dark energy is believed to drive the accelerated expansion of the universe, but its true nature remains mysterious. Is it possible that the conservation law is an approximation valid only within the boundaries of our current understanding? Imagine a universe where, in some remote corner, energy leaks into extra dimensions or interacts with quantum fields that we have yet to discover. In such a case, the energy we account for would be only a fraction of the true total. Our measurements would seem to obey conservation, while a hidden exchange occurs silently in the background. This notion challenges the idea that conservation of energy is an unbreakable law, suggesting instead that it might be an emergent property of our macroscopic world rather than a fundamental principle. Moreover, consider experiments in high energy, physics and cosmology where outcomes sometimes defy our conventional predictions. Could these anomalies be hints that energy is transforming in ways that go beyond simple conversion, perhaps even disappearing momentarily before reappearing in a different guise? If energy is not as immutable as we believe, then our entire understanding of the universe might be due for a profound revision. The law that never breaks paradox invites you to question what it means for energy to be conserved. Is it truly an absolute law, or merely a rule that holds under normal conditions, with exceptions waiting to be uncovered in extreme or hidden corners of reality? As you drift into sleep, let your mind wander through the possibilities. Ponder the vast, unseen currents of energy that may be flowing through the cosmos, challenging the very notion of what it means to exist. Level 23. The law of motion's memory momentum, the product of an object's mass and its velocity, is another cornerstone of physics. According to classical mechanics, momentum is conserved in a closed system, meaning that, barring external influences, the total momentum remains constant. Yet, the law of motion's memory paradox asks us to wonder, is momentum truly immutable, or could there be circumstances under which it is reversed or even seemingly forgotten? Consider a scenario where an object collides with another. In an ideal system, the momentum before the collision equals the momentum after. But what if, deep within the interactions, the momentum of one particle reverses direction unexpectedly, almost as if it remembered a previous state? Some quantum experiments have hinted at strange behaviors where particles appear to remember their past interactions, influencing their future motion in ways that seem to violate classical conservation. This idea challenges the very notion of momentum as a one-way, unalterable quantity. Now imagine if, instead of simply transferring momentum from one object to another, a system could momentarily store it, a kind of temporary memory that could later be released in reverse. Could this be a clue that momentum, like many aspects of quantum mechanics, is not as straightforward as classical physics suggests? In the realm of subatomic particles, where uncertainty reigns and wave functions collapse into definite outcomes, only upon observation, the idea of a memory of motion becomes plausible. Perhaps momentum is not merely conserved in a linear sense, but is part of a dynamic interplay between past and future states, a feedback loop in which information about motion is stored and retrieved. If momentum can be reversed, then it implies a deeper connection between time and motion, a relationship where the past can influence the future and vice versa. What if the universe carries a hidden ledger of every movement, a memory that occasionally rewrites the rules? This paradox encourages us to look beyond the rigid formulas of Newton and explore a universe where even momentum might bend its own rules under the right conditions. Let your thoughts wander as you relax, contemplating a world where the simple act of moving is intertwined with the echoes of what came before, a mystery that blurs the line between cause and effect, leaving us to wonder if our reality is more fluid than we ever imagined. Level 24. The energy motion. Link work and energy are two sides of the same coin, bound by the laws of physics that govern everything from the smallest particles to the largest galaxies. When you apply a force over a distance, you do work, and that work manifests as energy. This fundamental relationship is the engine behind all motion in our universe. But what if the link between work and energy is more mysterious than we ever believed? The energy-motion link paradox challenges the idea that work is merely the product of force and distance. In everyday life, when you push a box, you do work, and the energy you expend is measurable. Yet at the quantum level, where particles behave like both waves and particles, the conversion between work and energy becomes less clear-cut. The seamless transition of energy from one form to another, kinetic energy into potential energy and vice versa, suggests that these two aspects of motion are intrinsically connected. Consider a roller coaster. At the top of a hill, it possesses maximum potential energy, which then converts into kinetic energy as it descends. The total energy remains constant, but it transforms fluidly between forms. This elegant dance is the foundation of conservation laws. However, what if this dance sometimes takes unexpected steps? What if, in some situations, work can be done without a corresponding obvious force? If energy can be transferred in ways that defy our conventional calculations? Some theoretical models in physics propose that energy can be redistributed via mechanisms we have yet to fully understand. It might be that the energy in a system is not just a sum of its parts, but is also stored in the very structure of space-time. In this view, work is not solely about the interaction between objects, but about how the fabric of reality itself rearranges energy as it flows from one state to another. The energy-motion link challenges us to think beyond the obvious. It hints at a hidden network where energy and motion are interwoven into the very essence of the universe, an elegant interplay that, when fully understood, might reveal new dimensions of physics and even new ways to harness energy. As you drift into a calm and receptive state, let your mind explore this intricate relationship, pondering how every movement you make is a part of an eternal, interconnected dance that underpins all of existence. Level 25. The hidden mass. Center mass is a concept we take for granted, a fixed measure of how much stuff an object contains. We calculate an object's center of mass as the weighted average of its mass distribution, usually found inside the object's physical boundaries. But what if that center of mass could exist outside the object itself? Imagine a long, thin rod or an asymmetrical object where the distribution of mass is so uneven that its balance point lies beyond its visible limits. This seemingly paradoxical idea challenges our classical understanding of mass distribution and equilibrium. In everyday scenarios, the center of mass helps predict motion, stability, and balance. When you toss a ball or watch a gymnast perform a flip, the center of mass is what ultimately determines their trajectory and balance. In most cases, this point lies within the object, making calculations straightforward. However, in objects with irregular shapes or non-uniform density, the center of mass may lie outside the physical boundaries, a phenomenon that, while mathematically sound, seems almost magical. Consider, for example, a boomerang. Its curved shape and variable density allow it to fly gracefully through the air, balanced by a center of mass that isn't immediately obvious from its silhouette. This paradox invites us to question how deeply we understand stability and balance. Could there be systems where the hidden center of mass governs motion in unexpected ways? In advanced engineering and robotics, designers exploit these principles to create devices that maintain equilibrium through dynamic adjustments. Even in nature, certain plants and animals might leverage a displaced center of mass to optimize movement or stability. What if, on a cosmic scale, galaxies or nebulae exhibit similar properties, with their gravitational centers residing outside their visible structures? Such a possibility would compel us to rethink the gravitational interactions that hold the universe together. The hidden mass center paradox forces us to challenge our assumptions about where mass lives in an object and how that affects motion and stability. As you relax and drift into sleep, allow your thoughts to wander over this mystery. Perhaps what we see is only part of the story, and the true balance of the cosmos hides in unexpected, invisible places, guiding everything from the smallest particle to the largest galaxy. Level 26. The Gravity Center. Mystery gravity is the force that governs the motion of planets, stars, and galaxies. According to classical physics, every object exerts gravitational pull as if all its mass were concentrated at its center. But does gravity really pull from a single point, or does it emanate from every part of an object simultaneously? This is the gravity center mystery, a paradox that questions whether the gravitational force is as simple as a point mass, or if the reality is far more complex. Consider a perfectly uniform sphere. Its gravitational field can indeed be modeled as if all mass were concentrated at the center. However, most objects in the universe are not perfect spheres. They are irregular, with varying densities and shapes. In such cases, the gravitational pull isn't always straightforward. For instance, mountains, oceans, and even human-made structures create subtle variations in local gravity. This suggests that gravity might actually be a cumulative effect arising from every bit of mass, with no single center dictating its influence. Furthermore, modern theories in physics including Einstein's general relativity, show that gravity is the curvature of spacetime caused by mass and energy. In this view, gravity isn't a force acting from a pinpoint, but an effect spread throughout the warped fabric of space. The distribution of mass in an object contributes collectively to the gravitational field, making the concept of a singular center less meaningful. Imagine a sprawling galaxy. Its stars, gas, and dark matter interact gravitationally in such a way that the pull felt by an observer is the sum of countless individual contributions. This paradox challenges the simplicity of classical approximations. If gravity is truly a holistic phenomenon, then our understanding of how celestial bodies interact must be deeper than the conventional notion of a center of mass. It may be that every atom in an object contributes to the gravitational pull, creating a complex interwoven field that defies reduction to a single point. As you drift off to sleep, let your thoughts wander through the mystery of gravity, a force that binds us all, not from one isolated center, but from an intricate network of mass and energy spread across the cosmos. Level 27. The spin that never stops. Rotation is a familiar concept. Wheels turn, planets spin, and electrons orbit the nucleus. We believe that friction and external forces eventually slow down motion, yet in the vast vacuum of space, objects can continue spinning indefinitely. This is the spin that never stops paradox, a mind-bending notion that, in the absence of friction, rotation can be eternal. On Earth, friction is an ever-present force that drains kinetic energy. A spinning top gradually slows until it comes to a halt, losing energy as heat. But in the frictionless environment of space, there is nothing to sap an object's rotational energy. Planets and stars, once set in motion, continue to spin for billions of years. Even a tiny particle, free of air resistance and friction, could theoretically spin forever. This eternal spin challenges our understanding of motion. It suggests that rotation is a fundamentally different form of motion, one that, once initiated, requires no additional energy to sustain. Consider the pulsars, rapidly spinning neutron stars that emit regular pulses of radiation. Their incredible rotational speeds persist because the vacuum of space offers no resistance. Similarly, the galaxies themselves rotate gracefully through the cosmos, a cosmic dance that has been going on since the universe's infancy. Moreover, quantum mechanics introduces the concept of intrinsic spin, an inherent property of elementary particles that doesn't rely on classical rotation. Electrons, for example, have spin values that are fixed, contributing to the magnetic properties of atoms. These quantum spins are not subject to friction in the traditional sense, hinting at a universe where rotational motion is built into the fabric of existence. The spin that never stops paradox invites you to consider the nature of energy conservation in rotational systems. In a perfect vacuum with no friction or external forces, an object's spin is truly eternal, a silent, unending rotation that defines the cosmic rhythm. As you drift off, let your mind spin with the idea that in the vast, boundless space of the universe, everything may be in constant perpetual motion, each rotation a testament to the infinite, timeless dance of creation. Level 28. The mass that won't move mass is the measure of an object's resistance to changes in motion. It's inertia. In everyday life, when you push an object, you feel its weight and resistance, but on a cosmic scale, inertia takes on a whole new dimension. Imagine a massive celestial body, a star or a planet, moving through the vast vacuum of space. There's no friction to slow it down, so it continues its journey seemingly forever. Yet, inertia isn't just about mass. It's about how that mass interacts with the fabric of space and time itself. At the microscopic level, particles behave in ways that defy our intuitive understanding of inertia. In the quantum realm, an electron in an atom is not fixed in a single orbit but exists in a cloud of probability. It is as if inertia at these scales is less about resistance and more about potential, a latent capacity to respond when disturbed. Now imagine scaling this phenomenon up to cosmic proportions. A galaxy, composed of billions of stars, rotates and moves with momentum that appears immutable, the mass that won't move. Paradox challenges us to understand how inertia works when there's virtually nothing, no air, no friction, to slow things down. This paradox is especially fascinating when we consider that the universe is expanding. Galaxies recede from each other at tremendous speeds, yet they maintain their individual rotations and orbits. The hidden nature of inertia ensures that despite vast distances and minimal external resistance, the motion of massive objects remains consistent. It hints at an underlying cosmic order, an inertia that is built into the very structure of space-time. Perhaps in a universe governed by dark matter and dark energy, inertia is not solely a function of visible mass, but also of mysterious, unseen forces that hold everything in a delicate balance. If inertia is so deeply ingrained in the cosmic order, then what happens when it encounters a disruption? Could a sudden burst of energy from a supernova or a collision between galaxies momentarily alter the inertia of these colossal bodies? And if so, how does the universe recover and restore equilibrium? The mass that won't move paradox invites us to contemplate whether inertia, as we understand it, is an absolute property or a dynamic participant in the grand dance of the cosmos. As you relax and let your mind wander among the stars, consider that every planet's orbit, every star's spin, and every galaxy's journey is governed by this mysterious, unwavering resistance, an inertia that never falters, no matter how vast or empty the space it traverses. Level 29. The phantom torque is the rotational force that causes objects to twist or spin, an essential concept in mechanics. Typically, torque arises when a force is applied at a distance from an object's pivot point. But what if torque could exist without any obvious force acting upon it? Imagine a spinning wheel that suddenly accelerates its rotation without any external push, as if an invisible hand were at work. This is the phantom torque paradox, a mind-bending concept that challenges our conventional understanding of rotational dynamics. In classical mechanics, torque is straightforward. It's the product of force and the lever arm's length. Without force, there should be no torque. Yet, in certain quantum systems, particles exhibit angular momentum that appears to change state without any apparent external influence. Could this be evidence of a hidden torque, one that operates beyond the reach of our classical laws? The paradox deepens when we consider astrophysical phenomena. Some rotating celestial objects seem to alter their spin rates unexpectedly. Neutron stars and pulsars, for example, exhibit irregularities in their rotation that cannot be fully explained by conventional forces alone. These anomalies raise the possibility that a kind of phantom torque may be at play, subtly adjusting angular momentum without the classical push or pull we expect. Moreover, the idea of phantom torque might extend beyond physical objects to more abstract realms. Consider the concept of internal forces within complex systems. Could similar principles apply to the rotation of galaxies or even the swirling patterns of energy in quantum fields? In these cases, the torque might not be generated by an external force, but rather emerge from the intricate interplay of internal interactions that we have yet to fully grasp. If phantom torque exists, it could rewrite our understanding of rotational dynamics, suggesting that objects might change their spin rate without any external intervention. This would imply that the underlying rules of motion are more fluid and mysterious than previously thought, blending classical mechanics with quantum phenomena in ways that defy simple explanation. As you close your eyes and drift into sleep, let your mind ponder the possibility that the forces governing rotation are not always visible. Perhaps somewhere in the depths of the cosmos, a phantom torque is at work, quietly shaping the spin of distant stars and galaxies in an unseen dance that defies the laws of physics as we know them. Level 30. The infinite spin of motion spin, or angular momentum, is the rotational equivalent of linear momentum. In our everyday experience, objects eventually stop spinning due to friction or resistance, But in the near-frictionless vacuum of space, spin can persist seemingly forever. The infinite spin of motion paradox challenges us to consider what happens when angular momentum is not gradually dissipated, but instead continues endlessly, undeterred by external forces. Imagine a planet or a star rotating in the vast emptiness of space. With little to no friction to slow it down, its spin might last billions of years. On a smaller scale, consider a subatomic particle, an electron with an intrinsic spin that never changes, a constant property of matter. In both cases, spin is a fundamental characteristic that appears to be eternal. Yet, classical physics would predict that, given enough time, even the tiniest resistance would eventually sap all rotational energy. So why does spin endure? One explanation lies in the conservation of angular momentum. Once set in motion, an object will keep spinning unless acted upon by an external torque. In the vacuum of space, where resistance is virtually non-existent, there is nothing to slow down that rotation. The infinite spin of motion paradox thus reveals a universe where rotation is not just a transient phenomenon, but a persistent, eternal state, a cosmic dance that goes on forever. Furthermore, in the quantum world, particles have an intrinsic property called spin that is quantized. It exists in fixed, unchanging amounts. This spin is not due to any physical rotation in the classical sense, but is a fundamental attribute that defines a particle's identity. In this way, spin becomes an inherent part of the fabric of matter, immune to the wear and tear of time. What does it mean if spin is truly infinite? It suggests that, in the grand scheme of the universe, some forms of motion are not subject to decay. They persist as reminders of the initial conditions of the cosmos, echoing back to the very moment of creation. Whether it's the ceaseless rotation of a distant pulsar or the unchanging spin of an elementary particle, the infinite spin of motion challenges us to rethink the transient nature of movement. Level 31. The Law of Rotation. Angular momentum is one of the most reliable constants in physics. Once an object begins spinning, it tends to keep spinning unless an external torque intervenes. Yet in our everyday world, we see things that eventually slow down and stop. Consider a spinning top that gradually loses speed and falls, or a wheel that decelerates over time. This raises a compelling paradox. If angular momentum is strictly conserved in an isolated system, how do objects ever truly come to rest? In theory, conservation of angular momentum means that in the absence of external forces, like friction or air resistance, a spinning object would continue its rotation indefinitely. In the frictionless vacuum of space, celestial bodies such as planets and stars can maintain their spin for billions of years. However, on Earth, the omnipresent forces of friction and drag sap kinetic energy. When a spinning top encounters even a minute surface friction, it gradually loses angular momentum, and its rotation slows until it finally stops. But this process invites deeper questions. Is it the only way that angular momentum can be lost, or does it sometimes shift into forms that we cannot easily detect? Some physicists propose that what appears as a loss of angular momentum on a macroscopic scale may simply be a conversion of energy from organized rotational motion into disordered thermal energy. As a spinning object slows, friction converts its kinetic energy into heat, which is dispersed into the surroundings, effectively hiding the angular momentum. Even though the law of conservation holds true in closed systems, our open, real-world environments allow energy to dissipate into less noticeable forms. This raises the question, if we could capture and convert every speck of this dissipated energy back into angular momentum, would the object continue spinning? Moreover, there are extreme scenarios where angular momentum might be redistributed, rather than entirely lost. For example, during cosmic collisions or in turbulent astrophysical environments, angular momentum might transfer between interacting bodies, preserving the total momentum while individual spins vary dramatically. This intricate dance of rotation underlines that the conservation law operates on a universal scale, but its manifestation can appear altered when observed in smaller, everyday systems. In essence, the law of rotation paradox challenges us to Consider that while angular momentum is conserved overall, the forms in which it appears can transform significantly. The interplay between friction, energy conversion, and external interactions leads us to see objects slowing down, even though, in a perfect vacuum, they'd spin eternally. As you drift into a state of calm, let your mind ponder the mystery of rotation, how even the most steadfast laws of physics can seem to bend and shift in our imperfect real world. Level 32. The force that pulls inward. Centripetal force is the unseen hand that guides orbiting bodies, pulling them toward the center and keeping them on a curved path. It's what keeps the Earth circling the Sun and planets, dancing in their celestial orbits. But what if this inward pull were to suddenly disappear? How would objects behave if the force that anchors them vanished? In classical mechanics, centripetal force is the reason an object follows a curved trajectory rather than moving in a straight line. For a planet, this force is provided by gravity, a constant, albeit sometimes subtle pull that maintains orbital paths. However, consider a scenario where gravity or any other inward force suddenly weakens or vanishes. The object in orbit would no longer follow a curved path. It would instead move off in a straight line, shooting into space at the velocity it had at the moment of force loss. This raises profound questions about stability in our universe. Is the centripetal force an intrinsic property of motion in a curved space, or is it entirely reliant on external forces? Theories in general relativity show that massive objects warp spacetime, creating what we perceive as gravitational attraction. If this curvature were to change suddenly, the familiar orbits of celestial bodies would be thrown into chaos. Stars, planets, and moons might drift away, or conversely, crash into each other. On a more everyday scale, even simple objects in circular motion rely on centripetal force. A spinning bucket of water remains intact because the water is forced outward by inertia, while the bucket's handle provides the inward pull to keep it contained. If that inward force were to vanish, the water would fly outward in a dramatic burst, demonstrating how critical this force is to maintaining order. The force that pulls inward paradox invites us to imagine a universe without this unifying force, a cosmos where everything moves in straight lines, and the beautiful, predictable curves of orbits become chaotic, unbound trajectories. It challenges our intuition and makes us wonder if the stability we see is merely a delicate balance that could be disrupted at any moment. As you settle into sleep, let your thoughts wander to this possibility. Ponder the fragility of orbits and the mysterious force that holds the universe together. Level 33. The machines that defy gravity, simple machines, levers, pulleys, inclined planes, are designed to make work easier by redistributing forces. We use them every day to lift heavy objects or move things with less effort. But what if there were machines that not only defied gravity but seemed to break the very laws of physics? Imagine a contraption that, when activated, appears to levitate objects effortlessly, as if gravity itself has been neutralized. This isn't just about reducing friction or mechanical advantage. It's about bending the rules of gravitational pull. In our classical understanding, gravity is an inescapable force pulling all matter toward the Earth. However, advanced engineering concepts, such as magnetic levitation and superconductors, have demonstrated that under certain conditions, objects can float in midair. The idea behind these gravity-defying machines is to counteract gravitational force using opposing forces. For instance, magnetic levitation uses repulsive magnetic fields to keep an object suspended, effectively canceling gravity. But the paradox lies in how these machines seem to operate with a simplicity that defies the complex interplay of forces they must overcome. They appear to rewrite the rules, making it seem as though gravity is not a fixed, unyielding force, but something that can be negotiated, altered, or even bypassed entirely. This phenomenon challenges our understanding of energy and equilibrium. If a machine can defy gravity, then is it truly breaking the laws of physics, or merely exploiting hidden aspects of those laws that we have not yet fully understood. Perhaps gravity is not as absolute as we once thought, but a force that can be manipulated under the right conditions. This opens the door to revolutionary technologies, devices that could transform transportation, construction, and even space travel. The machines that defy gravity paradox invites us to reimagine the potential of human ingenuity. It forces us to question the limitations imposed by nature, to consider whether the laws we take for granted might be just guidelines waiting to be surpassed. As you drift off into sleep, allow your mind to explore these possibilities. Ponder. A future where gravity is not a barrier but a variable, one that can be adjusted by machines built on the cutting edge of physics. Level 34. The secret of mechanical power-mechanical advantage is one of the fundamental concepts in physics, allowing us to lift heavy objects with minimal effort. A simple lever can let a child lift a boulder, while a system of pulleys can make moving immense loads seem almost effortless. But is there a limit to mechanical advantage? Can we build a machine so efficient that it completely negates the need for force? At first glance, mechanical advantage seems almost like a cheat code for nature. By redistributing force over a greater distance, a lever, inclined plane, or pulley system reduces the effort needed to perform a task. This principle is behind everything from the gears in a bicycle to the hydraulics of massive cranes. Yet, despite their effectiveness, these machines do not create energy. They only transform it. The question arises, if mechanical advantage increases the force we can exert, could we build a machine with infinite power? In reality, there are limits. The laws of physics ensure that no system is 100% efficient. Friction, air resistance, and material constraints always impose restrictions. Even a perfect pulley system can't eliminate the need for input energy. It can only redistribute effort over a longer distance. This leads to an intriguing paradox. If mechanical advantage allows us to move immense loads, could there be a configuration that completely bypasses force altogether? In theory, perpetual motion machines, a concept long debunked, attempt to exploit mechanical advantage to produce unlimited energy. However, fundamental laws like the conservation of energy and entropy prevent such a reality, yet nature itself has found ways to maximize mechanical advantage. Consider the tendons and muscles in the human body acting as natural levers, amplifying force with incredible efficiency. Even the movement of celestial bodies follows similar principles, where gravitational interactions create orbital slingshots, boosting spacecraft without fuel. The secret of mechanical power reveals a profound truth. While mechanical advantage allows us to push the limits of efficiency, the universe still enforces strict boundaries. No machine can create energy from nothing, but through clever engineering, we can continue to unlock greater power than ever before. As you drift into sleep, let your mind explore the possibilities. What if the ultimate machine existed, one that rewrote the rules of physics entirely? Level 35. The harmony of oscillations. Everything vibrates. From the strings of a violin to the very atoms that make up our existence, oscillations are the heartbeat of the universe. But what if vibration itself was more than just a motion? What if it was a fundamental law connecting everything we know? Oscillation is the repetitive movement of an object between two positions, seen in pendulums, springs, and waves. On a larger scale, it governs tides, planetary orbits, and even the fluctuations of galaxies. But beneath this observable motion lies a hidden reality, one where vibration is not just a byproduct of motion, but a universal principle shaping existence itself. Consider sound waves, which travel through air by compressing and expanding molecules in rhythmic patterns. These waves transmit energy, allowing us to hear music, speech, and even the faintest echoes from across vast distances. Now extend this concept to light, which oscillates as an electromagnetic wave. The very act of seeing, hearing, and feeling. Heat is a result of oscillatory motion. But the mystery deepens when we enter the quantum realm. Particles once thought to be solid exhibit wave-like behaviors. The uncertainty principle suggests that particles vibrate between different states, never truly still. Even empty space is filled with quantum fluctuations, energy popping in and out of existence. Could it be that oscillation is not just a movement, but the underlying mechanism of all reality? If everything vibrates, does that mean there is an ultimate frequency, a cosmic rhythm that unites all matter? Scientists have found that different scales of the universe resonate with specific frequencies. Atoms vibrate at terahertz speeds, while planets oscillate in slow rhythmic orbits. Could this be the key to a unified theory? A single principle linking gravity, electromagnetism, and quantum physics? The harmony of oscillations suggests that the universe is not a static place, but a symphony of motion. As you drift into relaxation, imagine the unseen vibrations all around you, the pulsation of your heartbeat, the resonance of distant stars, the frequency of existence itself. Level 36. The hidden motion of the universe. When we think of motion, we picture cars speeding down highways, waves crashing against the shore, or planets drifting through space. But hidden beneath these everyday movements lies a deeper truth. 1. That connects sound, waves, and even quantum mechanics through the elegant principle of simple harmonic motion. Simple harmonic motion, SHM, is the smooth, repetitive oscillation of an object around an equilibrium point. The back-and-forth swing of a pendulum, the vibration of a guitar string, and the bouncing of a spring all follow the same mathematical patterns. At first, it seems like a simple concept, until we realize that this same motion governs the very fabric of reality itself. Take sound, for instance. Every musical note you hear is produced by an object oscillating at a precise frequency. Whether it's a singer's voice or the hum of a tuning fork, the air vibrates in wave-like patterns, carrying energy from one place to another. The same principles apply to water waves, light waves, and even the fundamental particles of the universe. But the real mystery begins when we examine quantum mechanics. At a microscopic level, even matter itself exhibits wave-like behavior. Electrons orbiting atoms follow harmonic patterns, and the universe's tiniest building blocks vibrate in ways we can barely comprehend. Could it be that all existence is just a series of waves, particles shifting between states in a constant, unseen rhythm? Even on a cosmic scale, simple harmonic motion appears in surprising ways. Stars oscillate as they expand and contract, pulsating with energy. Gravitational. Waves ripple across space-time, carrying the echoes of ancient cosmic events. The entire universe, from the smallest quark to the largest galaxy, appears to move in synchronized rhythmic patterns. This realization challenges our understanding of motion itself. If everything in existence follows simple harmonic motion, does that mean the universe has a natural frequency, a fundamental beat that drives all matter and energy? Some physicists believe that by discovering this ultimate oscillation, we may unlock secrets of time, space, and even consciousness itself. The hidden motion of the universe invites us to see reality in a new light, not as a collection of separate objects, but as a vast interconnected web of vibrations. As you drift into sleep, let your mind resonate with this idea. Everything, from your breath to the cosmos, moves in perfect harmony, a rhythm that never truly stops. Level 37. The mystery of waves look around you. Everything you see, hear, and feel may not be as solid as it appears. What if, at the most fundamental level, everything in existence is not a particle, but a wave? In classical physics, waves and particles were thought to be separate concepts. A wave was a disturbance that traveled through a medium, like ripples on a pond. A particle, on the other hand, was a tiny, indivisible unit of matter. But as scientists explored the microscopic world, they discovered something astonishing. Particles can behave like waves, and waves can behave like particles. This is known as wave-particle duality, a strange phenomenon in quantum mechanics. Light, which we once believed was purely a wave, can act like a particle called a photon. Electrons, which were thought to be tiny, solid particles, can spread out like waves, existing in multiple places at once until observed. If everything at the smallest scale exhibits wave-like behavior, then what does that mean for reality itself? Think about sound waves traveling through air, or electromagnetic waves carrying radio signals. Even your thoughts, transmitted through neurons, generate tiny waves of electrical activity. Could it be that every object, even your own body, is just a complex pattern of waves vibrating at different frequencies? Some physicists believe that all matter is just a standing wave of energy. This idea forms the basis of string theory, which proposes that the universe is made up of tiny, vibrating strings of energy. If true, then everything, from the atoms in your body to the largest galaxies, might just be an intricate symphony of waves interacting with one another. But if all existence is just waves, what is causing them to vibrate? And more importantly, is there an ultimate wave, one that connects everything in the universe? The mystery of waves challenges our understanding of reality. Perhaps the universe itself is not made of solid matter, but of infinite ripples in the fabric of existence, waiting to be understood. Level 38. The sound that creates reality. Close your eyes and listen. The hum of an engine, the rustle of the wind, the quiet rhythm of your own breath. Sound is everywhere. But what if sound is more than just a vibration? What if it has the power to shape the physical world itself? Sound is produced by waves traveling through a medium, air, water, even solid objects. But these waves do more than just carry noise. They carry energy, and energy has the power to move, shape, and transform. Matter. Consider cymatics, the study of how sound waves influence physical structures. When fine sand or water is placed on a vibrating surface, it arranges itself into intricate, symmetrical patterns. The higher the frequency, the more complex the design. This suggests that sound doesn't just travel, it organizes, structures, and even creates form. But could sound waves shape reality on a larger scale? Some scientists believe that early in the universe's history, sound waves rippling through primordial plasma played a role in structuring galaxies. Even today, sound waves travel through the sun, revealing secrets about its internal structure. Ancient cultures understood the power of sound. Many spiritual traditions believe that sound was the force that created the universe itself. In Hinduism, the sacred syllable Om is said to be the cosmic vibration that underlies all existence. In modern science, researchers are exploring how frequencies can heal the human body, repair damaged DNA, and even levitate objects. If sound has the power to move matter, does that mean we can unlock hidden forces through specific frequencies? Could there be a sound so powerful that it alters the very fabric of reality? The sound that creates reality forces us to rethink everything we know about the relationship between sound, energy, and the universe itself. Level 39. The secret frequency of the universe. Everything in existence has a natural frequency, a unique vibration that defines its existence. From the atoms in your body to the stars in the sky, each object resonates with its own hidden rhythm. But what if these frequencies are more than just a scientific curiosity? What if they hold the key to understanding the entire universe? The concept of natural frequency can be observed everywhere. When a singer hits the right note, they can shatter a glass, not because of force, but because the sound matches the glass's natural vibrational frequency. Bridges, buildings, and even planets have resonant frequencies, vibrating when they absorb energy at the right rate. But could there be a universal frequency? A hidden vibration that connects all things? Some physicists believe the entire universe hums with a cosmic resonance, a background frequency woven into space-time itself. This idea is echoed in ancient philosophies where certain frequencies were believed to align with the harmony of the cosmos. Consider the Schumann resonance, a set of electromagnetic waves that naturally occur in Earth's atmosphere, resonating at around 7.83 Hz. Some researchers suggest that this frequency influences human consciousness, possibly linking our biology to the rhythm of the planet itself. If everything vibrates at a specific frequency, could tuning into the right one unlock hidden potentials? Could sound, resonance, and frequency be the missing keys to unexplained phenomena, from telepathy to time travel? The secret frequency of the universe suggests that reality is not just a collection of separate objects, but a vast symphony of vibrations. If we could learn to hear the universe's hidden song, what secrets would it reveal? Level 40. The pulse of the cosmos. The universe is not silent. It pulses, vibrates, and moves in waves that ripple across time and space. But where do these waves come from? What force sets them into motion? From the tiniest atoms to the largest galaxies, everything in existence moves in rhythmic patterns. Scientists have discovered cosmic waves stretching across the fabric of space itself. Gravitational waves, remnants of massive cosmic events, bending space-time as they travel. These waves were first predicted by Albert Einstein in his theory of relativity and were finally detected a century later. But what if the universe has a deeper pulse, one we have yet to understand? The cosmic microwave background radiation, an ancient energy left over from the Big Bang, hums through space as a faint signal, an echo of the universe's birth. Some theorists even suggest that the universe itself oscillates, expanding and contracting in cycles, creating waves on a cosmic scale. Beyond the vastness of space, waves appear in quantum mechanics too. Particles exist in a wave-like state until observed, hinting that reality itself may be built upon hidden vibrations. Could the pulse of the cosmos be the foundation of all existence? If so, what controls this universal rhythm? Is it the fabric of space itself, a hidden energy field? Or something even stranger? The pulse of the cosmos reminds us that the universe is alive with motion, and its deepest mysteries may still be waiting to be uncovered. Level 41. The invisible pressure. You don't feel it, but right now, the air around you is pressing down with a force greater than you might imagine. Air pressure surrounds us at all times, yet we barely notice it. Why? And what would happen if it suddenly disappeared? Air is made up of countless tiny molecules moving in all directions, colliding with every surface, including your skin. At sea level, the weight of Earth's atmosphere creates a pressure of about 14.7 pounds per square inch. It's this pressure that allows us to breathe, keeps water from boiling at room temperature, and even affects how we experience weather. But we don't feel air pressure because it's balanced, pushing on us from all sides, inside and out. However, when that balance is disturbed, strange things happen. Ever noticed how your ears pop when you climb a mountain or take off in an airplane? That's because the air pressure outside your body is changing, but the pressure inside your body takes time to adjust. In extreme cases, rapid changes in air pressure can be deadly. In space, where there is no air, human blood would start to boil due to the lack of external pressure. Deep-sea divers, on the other hand, face crushing forces due to the immense weight of the water above them. But could there be an even deeper mystery to air pressure? Some physicists believe that pressure variations could be linked to hidden forces in the universe. Could air pressure itself be part of a greater force we don't yet understand? The invisible pressure is a force that shapes our world, yet we barely notice its existence until it changes. Level 42. The floating liquids. Secret: why does a rock sink in water, but a massive ship floats? Why do some liquids hold objects up while others let them fall? The answer lies in one of nature's most puzzling forces: buoyancy. Buoyancy is the force that makes objects float. It depends on two things: the weight of the object and the density of the liquid. If an object is denser than the liquid it's placed in, it will sink. If it's less dense, it will float. But there's something even stranger. Some liquids can make objects float that normally sink. For example, in the Dead Sea, swimmers float effortlessly because the water is packed with salt, making it denser than regular ocean water. Mercury, a liquid metal, is so dense that even a heavy chunk of iron can float on its surface. Why does this happen? When an object is submerged in a liquid, it displaces some of that liquid. The liquid pushes back with an upward force equal to the weight of the displaced fluid. This is known as Archimedes' principle. But if the liquid itself is heavy enough, even dense objects can stay afloat. Does this mean that, theoretically, there could be a liquid dense enough to make even a boulder float? Or what if there were substances that could change their density at will, defying the rules of buoyancy? The floating liquid's secret reveals that the ability to float isn't just about weight. It's about the hidden forces beneath the surface. And if we could master them, who knows what else we might learn to control? Level 43. The fluid that thinks. Fluids move, twist, and change shape in ways that seem almost intelligent. But can a fluid actually think? Could it have some form of memory or decision-making ability? At first, it sounds impossible. After, all fluids are just collections of molecules flowing together, but under the right conditions, fluids can behave in ways that mimic life. Certain liquids can remember past movements. Scientists have observed droplets of oil navigating mazes as if they were choosing the shortest path. But how? The answer lies in surface tension and molecular interactions. When a drop of liquid moves through a path, it leaves behind tiny changes in the surface it traveled over. The next drop follows these changes, appearing to learn from the previous one. But the mysteries go even deeper. Some non-Newtonian fluids change their behavior depending on how they're touched. Cornstarch mixed with water becomes solid when hit, yet flows like a liquid when moved slowly. Some materials act almost like living things, responding to their environment. Could this mean that fluids have some form of primitive intelligence? Could we design liquids that process information, like a liquid computer? If a simple drop of fluid can navigate a maze, could an entire river choose its path over time? Perhaps the answer is hidden in the complexity of fluid motion, where physics meets something that feels almost alive. Level 44. The secret of liquid motion. When you pour a glass of water, it seems simple, but look closer and you'll see something far more chaotic. Why do some liquids flow smoothly while others twist and swirl unpredictably? Fluid motion is one of the most complex topics in physics. At slow speeds, liquids behave in an orderly way, with smooth layers gliding over each other, but increase the speed and everything changes. The once smooth flow breaks apart into swirls, eddies, and turbulence, seemingly random patterns. But is this randomness truly random? Some scientists believe that fluid motion follows hidden mathematical rules. Even chaotic flows may have deep patterns, repeating in ways we don't yet fully understand. Weather patterns, ocean currents, and even the movement of blood through our veins all follow the strange and unpredictable rules of fluid dynamics. What if these hidden patterns could be controlled? Could we find a way to make turbulent flows predictable? Could we harness the chaos of liquid motion to create new forms of energy? Perhaps the secret of liquid motion isn't that it's unpredictable, but that we simply haven't unlocked its full potential yet. Level 45. The resistance of motion. Why does honey flow slower than water? Why do some liquids resist movement more than others? This is the effect of viscosity, the hidden force that controls how fluids move. Viscosity is what makes thick liquids, like syrup, flow slowly, while thin liquids, like alcohol, move easily. It acts like an internal friction, slowing objects down as they move through a fluid. This is why a ball dropped into honey sinks much slower than one dropped into water. But here's the real mystery. Can viscosity be negative? Could there be a fluid that speeds things up instead of slowing them down? It turns out this isn't just science fiction. In certain situations, fluids can reduce resistance instead of increasing it. Some fluids, called superfluids, have zero viscosity. They flow forever without slowing down, defying everything we know about motion. Liquid helium, when cooled to near absolute zero, becomes a superfluid, able to climb walls and escape containers without any resistance. But what if there were fluids that not only had zero resistance but actively increased motion? Imagine a liquid that made objects move faster the more they passed through it. Could we one day create a substance that acts as an anti-friction fluid, allowing motion to continue indefinitely? The resistance of motion is a force we take for granted, but if we could unlock its secrets, we might discover a whole new way to control movement itself. Level 46. The temperature illusion. Temperature is something we experience every day: warm sunlight, a cool breeze, the heat of a stove. We measure temperature with thermometers, yet its true nature is far more enigmatic than the numbers indicate. Is temperature an objective property of matter, or is it merely a perception, a relative sensation arising from the motion of particles? At its core, temperature is defined as the average kinetic energy of the particles in a substance. When particles move faster, the substance feels hotter. When they slow down, it feels cooler. But this definition, while useful, reduces temperature to a statistical measure rather than a fundamental entity. Consider two identical objects in completely different environments, one in a vacuum and one in an atmosphere. They might have the same kinetic energy on a microscopic level, yet our experience of their warmth can differ dramatically. This raises the question: does temperature exist independently of our perception, or is it constructed by our senses and instruments? Some physicists argue that temperature is indeed an emergent phenomenon, a macroscopic construct that arises from the collective behavior of countless particles. In this view, temperature isn't a basic property like mass or charge, but a way to describe the overall energy state of a system. It's like the mood of a crowd, a measurement of collective feeling rather than an intrinsic quality of any single person. Our thermometers, calibrated to our human perception, capture this mood of the particles, yet they may not reveal the full complexity of how energy is distributed. Furthermore, when we delve into extreme conditions, such as near absolute zero or in the heart of stars, the concept of temperature becomes even murkier. At absolute zero, particles have minimal motion, yet quantum mechanics shows that they still possess zero-point energy. In these cases, the traditional notion of temperature starts to break down. Is the chill of near absolute zero a true absence of energy, or just our limited ability to measure it? The temperature illusion paradox challenges us to reconsider what we mean by heat and cold. Are these qualities real, or do they exist only in the interplay between particles and our perception? As you relax and let your mind wander, contemplate that the temperature you feel might not be a fixed number but a subjective experience, a beautifully intricate illusion woven from the dance of particles and the lens of your own senses. Level 47. The mystery of heat. Heat is a familiar sensation. The warmth of a fire, the embrace of sunlight, the cozy comfort of a heated room. Traditionally, we define heat as the transfer of energy due to a temperature difference, fundamentally arising from the movement of particles. But what exactly is heat? Is it simply the sum of moving particles, or does it conceal a deeper mystery that defies our basic understanding of energy transfer? At its simplest, heat represents kinetic energy, the random, jostling motion of atoms and molecules. When these particles move faster, the substance feels hotter. But this explanation, while practical, might not capture the full essence of what heat truly is. In our everyday experiences, heat appears as a tangible force, capable of melting ice or driving engines. Yet, on a microscopic scale, the energy that constitutes heat is both elusive and unpredictable, following the strange rules of quantum mechanics. Consider how heat flows from a hot object to a cooler one, a process that seems straightforward, yet involves countless interactions and collisions at a subatomic level. Each collision transfers energy in minute, discrete packets. But what if these energy exchanges are not random at all, but part of a hidden order that orchestrates the behavior of matter? Some theories suggest that heat might play a role in the emergence of order from chaos, acting as a catalyst for chemical reactions and even the formation of life. Moreover, as we push the boundaries of temperature extremes, approaching absolute zero or experiencing the intense heat of stellar cores, the nature of heat transforms. Near absolute zero, particles still vibrate due to quantum fluctuations, a reminder that heat never truly disappears. In contrast, in the extreme heat of a supernova, energy is so intense that conventional concepts of matter break down entirely. These extremes challenge our conventional models and hint that heat is not merely a measure of motion, but a dynamic phenomenon with layers of complexity. The mystery of heat invites you to look beyond the surface of everyday warmth and ponder the intricate dance of particles that underlies every spark of energy. It asks whether the heat you feel is just a byproduct of movement, or if it is a window into a deeper, more enigmatic process that shapes our universe from the ground up. Level 48. The law that controls everything. The laws of thermodynamics have long been considered the unbreakable rules governing energy and its transformation. They tell us that energy cannot be created or destroyed, only transformed, and that, in any process, some energy becomes unusable due to increased entropy. But what if these laws, so fundamental to our understanding of the universe, have exceptions? Could there be scenarios where these supposedly ironclad principles bend, twist, or even break entirely? The first law of thermodynamics, the conservation of energy, asserts that the total energy of an isolated system remains constant. The second law states that entropy, the measure of disorder, tends to increase over time, setting a direction for all natural processes. These laws are the pillars upon which our understanding of physics is built, from powering our engines to predicting the fate of stars. Yet, as we peer deeper into the quantum realm and cosmic phenomena, anomalies begin to appear. For instance, certain processes in quantum mechanics seem to violate classical expectations. Particles can tunnel through barriers, seemingly bypassing the conventional transfer of energy. Some experiments suggest that at very small scales, energy fluctuations occur that challenge our traditional notions of conservation. Could these quantum effects hint at exceptions to thermodynamic laws, or are they simply misinterpretations of phenomena that occur outside our standard frames of reference? Moreover, in the vastness of the cosmos, dark energy and dark matter play roles that are not fully explained by classical thermodynamics. The accelerating expansion of the universe implies that there might be hidden energy reservoirs or mechanisms at work that do not neatly conform to our established rules. Could it be that our laws of thermodynamics, while remarkably robust, are only approximations of a far more complex reality? A reality where the rules might be different under extreme conditions or in alternative dimensions. The law that controls everything. Paradox challenges us to imagine a universe where our most trusted principles are not absolute, but malleable. It forces us to consider whether energy transformations and entropy increases are truly universal, or if there exist rare moments when nature defies its own guidelines. As you let your mind drift into sleep, ponder the possibility that even the laws of physics might hold secrets yet to be unveiled, mysterious exceptions that could one day revolutionize our understanding of the cosmos. Level 49. The energy that cannot be created. Energy is a fundamental property of our universe, and one of the most sacred principles of physics is its conservation. It can neither be created nor destroyed, only transformed from one form to another. But this raises a profound question. If energy is conserved, where did all of it come from? Imagine the universe as a vast eternal reservoir of energy that simply is. Every flash of lightning, every burst of star formation, every tiny spark in your body is merely a transformation of energy that has always existed in some form. Yet this notion challenges our understanding of beginnings. The Big Bang Theory tells us that the universe expanded from a singular, incredibly hot and dense point. But if energy has always been present, was it simply rearranged at the moment of creation? Perhaps the universe didn't create energy at all. It merely changed its state. Some theories propose that energy exists as an inherent aspect of space-time woven into the very fabric of the cosmos. In this view, the total energy of the universe is a constant, balanced out by positive energy in matter and negative energy in gravitational fields. This delicate equilibrium means that while energy appears abundant, its net sum might even be zero. A cosmic balance sheet that has been maintained since the dawn of time. As you settle into sleep, consider that every star, every galaxy, and every living being is part of this endless energy cycle, merely shifting forms as the universe evolves. Yet the mystery remains. If energy is neither created nor destroyed, then what mechanism initiated the universe's dynamic processes? Could there be hidden aspects of energy that we are yet to comprehend? The conservation law is one of the most robust principles in physics, but its true origins and implications continue to inspire debate and wonder. In pondering this paradox, we are invited to look beyond our everyday experiences of energy as something that powers machines and fuels life, and to imagine it as an eternal, omnipresent force, a silent constant in an ever-changing cosmos. Level 50. The heat that disappears. Heat is the energy that flows from one body to another, often perceived as the warmth that fills a room or the heat released when fuel burns. According to the second law of thermodynamics, entropy, a measure of disorder, always increases, suggesting that energy should disperse and lead to a warming, chaotic state. Yet in many systems, we observe the opposite. Objects and environments become colder, not hotter. This phenomenon raises a fascinating paradox. If entropy always increases, how do some systems end up getting colder over time? In our daily life, cooling is achieved by transferring heat from a warmer object to a cooler one until equilibrium is reached. Refrigerators, for instance, extract heat from the inside and expel it outside, making the interior cold. But beyond these engineered systems, natural processes also exhibit cooling. For example, during nighttime, the Earth radiates heat into space and temperatures drop even though entropy increases overall. This suggests that the flow of heat is not always straightforward. It can be directed, controlled, and even reversed in localized regions, while the total disorder of the universe still climbs. At a deeper level, the paradox challenges our perception of heat as merely the kinetic energy of particles. In certain cases, energy is transformed so efficiently that systems appear to lose heat without a noticeable source of work. Consider phenomena like evaporative cooling, where liquid molecules at the surface escape into the air, taking their energy with them and leaving the remaining substance cooler. Such processes highlight that heat can vanish from a system even as the energy is redistributed elsewhere, adhering to the conservation law but defying our intuitive understanding of warming. Thus, the heat that disappears paradox invites us to contemplate the complexity of energy transfer. It prompts us to see that while entropy increases on a universal scale, local systems can indeed become colder through dynamic and efficient energy exchanges, an elegant interplay between the microscopic and macroscopic worlds that keeps our universe in balance. Level 51. The charge that powers everything. Electric charge is one of the fundamental properties of matter, underpinning the very structure of atoms and the forces that hold them together. It is the unseen engine that drives chemical reactions, fuels electrical currents, and governs the behavior of particles on the smallest scales. Yet the most captivating aspect of charge is its dual nature. Opposite charges attract, while like charges repel. But why do opposite charges always draw together? What is it about the nature of charge that creates such a powerful, almost magnetic pull? At the atomic level, electrons, negatively charged, are drawn to protons, positively charged, within the nucleus, creating a stable structure that forms the basis of all matter. This fundamental attraction is the reason molecules form, and it is crucial for the existence of life. The interplay of forces between opposite charges drives the creation of chemical bonds, turning individual atoms into complex structures that make up everything from water to the proteins in your body. The charge that powers everything paradox not only emphasizes this attractive force, but also asks us to consider its origins. Why do like charges repel so strongly? And what hidden principles determine the magnitude of these interactions? The electromagnetic force, described by Coulomb's law, shows that the force between two charges is inversely proportional to the square of the distance between them. This elegant relationship underpins everything from the behavior of everyday objects to the interactions of cosmic bodies. Moreover, the very existence of charge has profound implications for our universe. It is responsible for the flow of electricity that powers our modern world, the light emitted by stars, and the very structure of matter. Without charge, atoms would not form, and the universe would be a vastly different, unstructured place. Yet, despite its omnipresence, the nature of charge remains enigmatic. Its origins and behavior still spark questions among physicists. As you settle into a calm state, consider that the invisible pull between opposite charges is more than just a scientific fact. It is a force that literally powers everything around us, from the tiniest particles to the grandest galaxies, weaving the fabric of reality with its magnetic embrace. Level 52. The hidden force of Coulomb's law tells us that the force between two charged particles is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. This elegant equation has long been considered a pillar of electromagnetism, governing everything from the behavior of atoms to the forces that keep molecules together. But what if this force isn't as constant as we believe? What if the force between charges has hidden nuances that vary under different conditions, revealing a deeper layer of nature's complexity? Imagine a scenario where two charged particles interact in an environment where the medium isn't uniform, where temperature, pressure, or even electromagnetic fluctuations subtly alter the force between them. In such a case, the repulsion, or attraction we take for granted, might not follow the simple inverse square law precisely. Instead, it could shift dynamically, hinting at a hidden force that modifies Coulomb's constant depending on the local conditions of space-time. This idea challenges our basic assumption that the interactions between charges are fixed. It suggests that at a fundamental level, the forces that bind atoms or drive electricity might be influenced by factors we have yet to fully understand. In extreme environments, such as near a magnetar, inside a plasma, or within a rapidly fluctuating quantum field, the effective force between charges could deviate from its standard value. Such deviations might be subtle, detectable only through precision experiments, or they could be profound enough to influence the behavior of matter on a cosmic scale. The hidden force of Coulomb paradox invites us to consider that our neat equations might be approximations of a far richer underlying reality. It raises the possibility that the forces which hold our universe together are dynamic, evolving with the conditions of the cosmos rather than remaining static and unyielding. If the force between charges isn't constant, then the energy stored in electromagnetic fields and the behavior of electrical circuits might be more variable than we assume. This could lead to unexpected phenomena in materials science, energy transfer, and even in the stability of matter itself. In essence, exploring this paradox might open a new chapter in our understanding of electromagnetism, revealing hidden variables that tweak the basic interactions we've long taken for granted. Level 53. The field that is everywhere, the electric field, is an invisible force field that surrounds every charge, permeating even the emptiest of spaces. According to classical physics, even a vacuum isn't truly empty. It is filled with an electric field that can exert forces on charges that enter it. But what if the field that exists everywhere is more than just a passive backdrop? What if it is a dynamic, ever-changing canvas that influences the very nature of reality? Every charge generates an electric field that spreads out in all directions. In the simplest cases, these fields follow predictable patterns, their strength diminishing with distance. However, imagine a scenario where these fields interact in complex ways, merging, reinforcing, or even canceling each other out. In regions far from any obvious sources, the electric field might seem uniform, yet subtle fluctuations and variations could hide beneath the surface. These hidden ripples may affect the behavior of particles, influencing energy transfer, motion, and even the formation of matter on both micro and cosmic scales. In the quantum world, empty space teems with activity. Virtual particles constantly pop in and out of existence, and the electric field may play an active role in mediating these ephemeral events. Some theories even propose that the fabric of space itself is woven from fluctuating fields that give rise to the observable forces of nature. In such a view, the field that is everywhere isn't merely a static backdrop. It is a dynamic entity that shapes and is shaped by every charge, every photon, and every particle in the universe. This paradox encourages us to see the vacuum not as a void, but as a stage where the drama of creation and destruction unfolds continuously. As you contemplate the pervasive nature of the electric field, consider that even when you're in complete darkness or silence, this invisible force hums quietly around you, influencing the behavior of matter in ways that might one day unlock the secrets of energy and existence. Level 54. The potential that lies within. Potential energy is the energy stored within a system waiting to be unleashed. Traditionally, we associate potential energy with the presence of forces, like gravitational potential energy due to an object's position or electrical potential energy arising from a charge in a field. But what if potential energy could exist even in the absence of an obvious charge or force? What if there were hidden stores of energy embedded in the very fabric of space that remain untapped until conditions change? In classical mechanics, potential energy is defined relative to a reference point. A ball held high above the ground possesses gravitational potential energy because of its position, ready to convert into kinetic energy when dropped. Similarly, a charged particle held within an electric field has potential energy that can be released as it moves. But consider the possibility that potential energy is not solely confined to such scenarios. Perhaps beneath the surface there exists a latent energy in empty space, a dormant reservoir waiting for the right moment to be activated. Some modern theories propose that the vacuum is not truly empty, but filled with fluctuating fields and virtual particles. In these conditions, potential energy may be stored in the subtle configuration of these fields, independent of any specific charge or mass. This hidden potential might not manifest until the vacuum undergoes a phase transition or interacts with external forces, releasing bursts of energy that challenge our conventional energy conservation laws. The idea that potential energy lies within even without an explicit force questions our fundamental assumptions about how energy is stored and released. It suggests that what we measure as potential energy might just be the tip of an iceberg, a visible effect of a far more complex, underlying energy landscape that permeates every corner of the cosmos. As you ponder this mystery, consider that the energy you think is stored might be dynamically interacting with the quantum fields that fill the universe, waiting for the precise moment to transform into visible motion. Level 55. The storage of electricity capacitors are among the most intriguing components in electrical engineering. They store electrical energy in a way that seems almost magical, capturing and holding charge until it is needed, then releasing it in a controlled burst. But what truly happens inside a capacitor? At first glance, it appears to be a simple device. Two conductive plates separated by an insulator, accumulating charge on each plate when connected to a voltage source. However, beneath this basic design lies a world of complex interactions that reveal much about the nature of energy storage and transfer. Inside a capacitor, when voltage is applied, electrons are forced onto one plate, while leaving a deficit on the opposite plate, creating an electric field across the dielectric. This electric field is the key to its energy storage capability. The energy is stored in the field as potential energy, and its magnitude depends on the capacitance, determined by the plate area, the distance between them, and the properties of the dielectric material. Advanced capacitors use exotic materials to increase capacitance, squeezing more energy into a smaller space. As you delve deeper, consider the microscopic picture. At the atomic level, the dielectric becomes polarized. The molecules within it align with the electric field, effectively reducing the field's strength and allowing more charge to be stored for a given voltage. This dynamic interaction between the charge on the plates and the polarization of the dielectric is what makes capacitors so efficient in certain applications. Energy is not stored as moving electrons, but as the potential energy of the electric field. a subtle shift that occurs without any direct motion of charge across the dielectric. Furthermore, capacitors play a crucial role in smoothing out voltage fluctuations in circuits, acting as buffers that release energy when the supply dips and absorb it when there's a surplus. They are the unsung heroes in everything from power supplies to signal processing, silently ensuring that devices run smoothly. Yet, despite their widespread use, many of the details of how capacitors store energy remain a subject of active research, especially as engineers explore nanomaterials and quantum effects to design the next generation of energy storage devices. The storage of electricity paradox challenges us to look beyond the simple schematic diagram. It asks us to consider the invisible forces at work, the alignment of dipoles, the creation of electric fields, and the hidden energy waiting to be unleashed. As you let these ideas settle, imagine the capacitor as a tiny, controlled universe, where energy is stored in a delicate balance, ready to transform and power the world when the moment arrives. Level 56. The motion of charge. Electricity flows through our devices, powers our homes, and lights up our world, yet we never truly see it in action. The motion of charge paradox delves into the mystery of how charge moves in ways that are invisible to our senses. While we rely on wires and circuits to transport electrical energy, what happens at the microscopic level is a fascinating dance of electrons that defies everyday perception. When a voltage is applied to a conductor, electrons begin to drift in a specific direction. However, they do not move in a smooth, orderly line. Instead, their motion is chaotic, a result of countless collisions with atoms in the material. These electrons, while individually unpredictable, collectively create a steady current that powers our modern world. The apparent calm of a constant current masks the turbulent journey each electron undertakes, bouncing off impurities and lattice vibrations, a process known as scattering. In this hidden realm, charge flows like a river that is both erratic and precise. The net movement of electrons gives rise to current, but this flow is underpinned by quantum mechanics. Electrons exist in wave-like states, meaning they are not localized in one position until measured. This probabilistic behavior suggests that the motion of charge is not as straightforward as classical physics once taught us. Instead, it is a complex interplay of probability, energy levels, and quantum tunneling, where electrons can pass through barriers that would be insurmountable under classical laws. Moreover, phenomena such as superconductivity illustrate that, under certain conditions, charge can flow without resistance at all. In superconductors, electrons pair up into what are called Cooper pairs, allowing them to move in a coordinated, frictionless manner. This state of matter challenges our understanding of the everyday motion of charge, hinting at the deeper, hidden possibilities of electron behavior when external disturbances vanish. The motion of charge paradox invites us to consider that the electricity we depend on is not a simple, linear stream, but a rich tapestry of dynamic, microscopic interactions that continue to surprise scientists. As you allow your mind to relax and drift, ponder the unseen dance of electrons, a hidden world where chaos and order blend into the constant pulse of modern life. Level 57. The circuit that never ends. Electric circuits are the backbone of our modern technology, providing a path for electricity to flow and perform work. We design circuits to power devices, process signals, and perform calculations. But what if there were a circuit that could theoretically continue flowing forever without any energy input, a self-sustaining loop that defies the usual rules of energy consumption? This is the circuit that never ends paradox, a concept that challenges the idea that energy must always be supplied to maintain electrical flow. In our everyday world, every circuit eventually loses energy due to resistance, friction, and electromagnetics, radiation, which manifest as heat. Even in highly efficient superconducting circuits, energy is conserved, but real-world imperfections always cause a gradual decay of current. Imagine a hypothetical circuit in a perfect vacuum, constructed from materials with zero resistance, where no energy is lost to friction or heat. In theory, once initiated, the current in this circuit could flow indefinitely. Yet even this idealized scenario is challenged by the laws of thermodynamics and quantum mechanics. Tiny fluctuations, quantum noise, thermal vibrations, and even the gravitational influence of distant masses might slowly sap the energy of the system. Scientists have long dreamed of perpetual motion, a machine that could run forever without external energy, but every attempt has met with the unyielding wall of energy conservation. However, the circuit that never ends paradox pushes us to re-examine these laws. Could there be a way to create a closed loop where energy is not lost, or perhaps is continuously recycled? In the realm of superconductivity, electrons move in pairs with virtually zero resistance, hinting at the possibility of near-perpetual currents in controlled environments. But the true mystery lies in the concept itself. If a circuit could operate forever, what would it mean for our understanding of energy, work, and the very structure of physical law? Such a circuit challenges our conventional thinking and invites us to explore the boundaries of physics, where even the most established principles might be more flexible than we once thought. As you drift off, let your mind imagine this endless circuit, a silent, perpetual flow of electricity that defies decay, a symbol of the eternal energy pulsing at the heart of the universe. Level 58. The battle between AC and DC electricity flows in two distinct forms: alternating current, AC, and direct current, DC. At first glance, one might assume one is simply more powerful or efficient than the other, but the reality is far more nuanced. DC flows in a constant unidirectional stream, much like water steadily flowing through a pipe. It's the kind of current you find in batteries, solar panels, and electronic devices, offering a stable and predictable supply of power. On the other hand, AC reverses its direction periodically, a dynamic oscillation that makes it easier to transform between different voltage levels. This is why AC became the dominant method for power transmission over long distances. Its ability to be stepped up and stepped down efficiently minimizes energy loss over sprawling electrical grids. Yet, the battle is not simply about efficiency. DC has the advantage when it comes to electronic circuits and precision applications, where a steady voltage is critical. In contrast, AC's rhythmic flow can be harnessed for generating and distributing energy on a massive scale. In recent years, however, technological advancements have rekindled the debate. With the rise of renewable energy sources, high-voltage DC transmission is gaining popularity due to its reduced line losses over very long distances. This resurgence poses the question, is one form truly superior, or are they simply different, tools suited to distinct applications? The answer may lie in understanding that both AC and DC have unique properties that are optimal under specific conditions. While AC's ability to change voltage levels easily makes it ideal for power distribution networks, DC's stable nature is crucial for the inner workings of modern electronics. Engineers now often combine the strengths of both, using AC for grid-level power and converting it to DC for end-use in devices. In this ongoing battle, the superiority of AC versus DC becomes less about one form winning outright and more about the synergy of complementary technologies. As you relax and let these thoughts settle, consider that the true marvel lies not in choosing one over the other, but in how the interplay between AC and DC has powered the modern world, transforming our way of life in ways that continue to evolve with new innovations. Level 59. The field that bends reality. Magnetic fields are invisible forces that permeate our universe, shaping the behavior of charged particles and influencing the formation of cosmic structures. But what if these fields do more than just affect objects? They actually bend the very fabric of reality. Consider how magnets can alter the trajectory of a moving object or create levitation through repulsion. At a fundamental level, magnetic fields interact with electric charges to form electromagnetic forces that are essential for nearly every phenomenon we observe. In astrophysics, magnetic fields are responsible for phenomena such as solar flares, auroras, and the formation of accretion disks around black holes. These fields are not static. They twist, tangle, and evolve over time, influencing the structure of galaxies and even the behavior of interstellar gas. In the laboratory, magnetic fields guide plasma and fusion reactors and play a key role in advanced imaging techniques like MRI. Now, imagine a magnetic field so intense that it warps space-time, a concept predicted by general relativity. In regions near magnetars, the magnetic field can be billions of times stronger than Earth's, bending light and matter in ways that challenge our understanding of physics. These extreme environments suggest that magnetic fields may not merely influence reality, they might actually shape it, carving out paths for energy and matter in the cosmic dance. The field that bends reality. Paradox invites us to envision a universe where the unseen magnetic forces are not mere background players, but dynamic architects of existence. As you sink deeper into relaxation, let your mind explore the idea that the familiar world is molded by invisible fields that twist, fold, and ultimately define the structures of galaxies, stars, and even the atoms within. Level 60. The force of induction. Electromagnetic induction is a phenomenon that has revolutionized the way we harness energy, making it possible to generate electricity by simply moving a conductor through a magnetic field. Yet, the underlying mechanism of induction is as mesmerizing as it is practical. When a conductor cuts through magnetic field lines, an electric current is induced within it. This is the fundamental principle behind generators, transformers, and many modern electrical devices. But how does this process truly work? At its core, electromagnetic induction is governed by Faraday's law, which states that a change in magnetic flux through a circuit induces an electromotive force. This law explains why electricity can be produced without any physical contact between moving parts and magnets, as in the case of wireless charging systems. It is a subtle interplay of moving fields and conductive materials, a hidden dance that transforms motion into electrical energy. In everyday life, we see the effects of induction when we switch on a light or charge our phones. However, the real wonder lies in the invisible transfer of energy that occurs at the microscopic level. Imagine a magnetic field oscillating around a coil of wire, generating a current so precise that it can power entire cities. This conversion of energy is not only efficient, but also awe-inspiring, demonstrating the universe's ability to transform kinetic motion into usable power. The force of induction challenges us to think about energy in a new light. It shows us that motion isn't just movement. It is a dynamic force that can be harnessed to create electricity, drive motors, and even operate complex machines without direct contact. As you relax into the night, consider that every time you flip a switch or watch a turbine spin, you are witnessing the silent, powerful process of electromagnetic induction, a phenomenon that encapsulates the hidden beauty of the universe's energy cycle. Level 61. The charge that never rests. Electric charge is the cornerstone of electricity, and it flows relentlessly, even when you sleep. Every electron within you is in constant, ceaseless motion, creating an unseen current that underpins every thought and movement. But have you ever wondered what it means for charge to never rest? In the microscopic world, electrons do not simply sit still, they are forever buzzing around, driven by thermal energy, quantum fluctuations, and electromagnetic interactions. This perpetual motion is not only the reason your body conducts electrical signals, but it also forms the basis for all the devices and technologies that power modern life. At the atomic scale, electrons exist in a cloud of probability, constantly shifting positions around the nucleus. This motion is so intrinsic that even in a state of apparent stillness, like during sleep, electrons continue to dance in an unending ballet of energy and momentum. Their continuous movement generates magnetic fields and electrical currents, quietly maintaining the balance of energy within every cell. The charge that never rests. Paradox invites us to consider that what we perceive as rest is simply a state of equilibrium, where microscopic activity is hidden from our senses. Moreover, this relentless motion has profound implications for how we understand energy conservation and entropy. Every moving electron contributes to the overall energy flow of a system, ensuring that energy is always present, albeit in constantly transforming forms. It is this dynamic behavior that powers neural networks, fuels chemical reactions, and drives the processes of life itself. As you relax, allow your mind to wander through the hidden currents within you, realizing that even in moments of calm, an endless stream of charge is at work, weaving the fabric of existence. The mystery deepens when we consider that electrons, although moving continuously, do not lose energy in the classical sense. Instead, their behavior is governed by quantum mechanics, where probability and uncertainty reign. This means that the seemingly chaotic motion of electrons is actually a highly regulated process, ensuring that they never truly rest, but always contribute to the unseen energy of the universe. The charge that never rests challenges us to see that life is powered by a constant, vibrant energy, an eternal flow that, even in sleep, never ceases to move. Level 62. The law that holds atoms together. The structure of matter is built on a delicate balance of forces, and the law that holds atoms together is one of the most fundamental in physics. At its core lies Coulomb's force, the attractive force between oppositely charged particles. Without this force, protons and electrons would not coalesce to form atoms. Matter as we know it would simply dissolve into a chaotic sea of charged particles. Within an atom, electrons are drawn toward the positively charged nucleus by Coulomb's force, creating stable orbitals that define the element's properties. This invisible glue ensures that atoms maintain their structure, allowing them to bond into molecules and, ultimately, form the vast diversity of substances in our universe. However, the law that holds atoms together paradox challenges us to explore deeper. Is this force absolute, or does it vary under extreme conditions? In high-energy environments, such as in the cores of stars or during nuclear reactions, the balance between the attractive force of the nucleus and the repulsive force among protons becomes a critical factor. Small changes in these forces can lead to dramatic differences in the stability of matter. Even minute fluctuations in the electromagnetic field or quantum effects may alter the behavior of atoms, hinting that the very law holding them together might be more dynamic than previously believed. Furthermore, advanced theories suggest that the mass of particles, and hence their interactions, might emerge from their coupling with fields like the Higgs field. This implies that the force binding atoms is not an isolated phenomenon, but part of a complex interplay of fundamental forces. Such perspectives challenge the notion that Coulomb's force is fixed, opening the possibility that in some exotic conditions, the bonds holding atoms together might shift, leading to new states of matter. As you relax, contemplate the incredible forces that assemble the building blocks of existence. The law that holds atoms together isn't just a static rule. It is a dynamic interplay that has shaped the cosmos since the beginning of time, maintaining the order within the universe even as it evolves. Level 63. The field that touches everything. The concept of a field in physics is one of the most profound, an invisible entity that permeates space and interacts with matter. The electric field, for example, exists around every charge, influencing other charges even at great distances. The field that touches everything. Paradox invites us to consider that these fields are not merely background phenomena, but active participants in the unfolding of reality. An electric field is generated by charged particles and extends outward, influencing everything within its reach. Even in what we call empty space, this field persists, a silent force that shapes the behavior of particles. Its presence means that no space is truly empty. Every point in the cosmos is imbued with energy and potential. The field is the medium through which forces are transmitted, making it a crucial component in everything from electromagnetic radiation to the delicate operations of quantum mechanics. Moreover, these fields are dynamic. They change, fluctuate, and interact with each other in ways that can produce astonishing effects, such as the generation of electromagnetic waves, which allow us to communicate across the universe. The field that touches everything challenges our notion of separateness. Rather than seeing the world as a collection of isolated objects, we begin to view it as a continuous fabric, woven together by fields that subtly influence every particle, every molecule, every ray of light. In this view, the boundaries between objects blur, for they are all immersed in the same all-pervading fields. This interconnectedness hints at a deeper unity in the universe, a cosmic tapestry where everything is linked by these invisible forces. Even when you're asleep, the field is there, interacting with your body and the world around you, quietly shaping the processes of life and energy. As you drift into a state of calm, let your mind absorb the idea that nothing exists in isolation. The field that touches everything is a reminder that the universe is a living, dynamic system, a network of forces that binds all matter and energy in an intricate dance, from the smallest subatomic particles to the grandest galaxies. Level 64, the potential that awakens energy. Voltage is more than just a number on a meter. It is the hidden force waiting in the wings, ready to transform into kinetic action, much like a spark of inspiration in the mind. Imagine a quiet moment before a burst of creativity. There's an unseen potential that, once released, can change everything. In physics, voltage represents the potential difference between 2 points, a measure of the energy stored per unit charge. It is this potential that drives electrons to move, turning static energy into a powerful current. Every capacitor, battery, and power supply operates on this principle. They store energy in a dormant state until conditions are right for a release, a surge that can light up cities, drive motors, or power the smallest microchip. In a similar way, our thoughts and emotions are filled with potential. A single idea, once ignited, can spark a chain reaction that transforms our lives. The potential that awakens energy is a reminder that latent power exists in everything, waiting for the moment it is called upon. In many modern technologies, voltage is harnessed to perform work. The potential difference between the terminals of a battery drives electrons through a circuit, creating the current that powers our devices. But what if we could tap into even more subtle sources of voltage? Some researchers are exploring how nanomaterials and quantum effects can store and release energy in ways that defy classical expectations, opening up new frontiers in energy, efficiency, and storage. Consider also the natural world. Lightning is nature's dramatic demonstration of voltage in action, a sudden massive discharge of energy built up in storm clouds. This awe-inspiring phenomenon shows us that even the sky is charged with potential, waiting for the right moment to awaken. In this way, voltage becomes not only a technical parameter but a poetic symbol of hidden energy, the dormant force that, when unleashed, creates wonder. As you let your mind drift into a state of deep relaxation, ponder the potential that exists in every moment of your life, the energy waiting within you, ready to be awakened. Just as voltage drives electrons to create light and motion, so too can the latent power within your thoughts ignite a transformative journey. The potential that awakens. Energy invites you to see that every spark, every idea, carries the promise of change, a reminder that nothing remains dormant forever. Level 65. The invisible storage of power. Capacitors are silent powerhouses in the world of electronics. They store electricity in a manner that is both elegant and mysterious, much like the way our minds preserve memories without visible trace. A capacitor consists of 2 conductive plates separated by an insulating material, which, when charged, creates an electric field. The stored energy is held in reserve, ready to be released when needed, a hidden reservoir of power that transforms the way circuits function. The invisible storage of power is more than a technical concept. It's a metaphor for the unseen, potential that resides in every corner of the universe. In a capacitor, energy is not visible to the naked eye, yet it is there, waiting to energize a circuit when the conditions are right. The ability to store power in such a compact form has revolutionized modern technology, from smoothing out the fluctuations in power supplies to enabling the rapid discharge required in camera flashes. On a deeper level, this principle reminds us of how memories work in the human brain. Memories are stored in a complex network of neurons, hidden from view yet capable of being recalled to shape our experiences and decisions. Just as a capacitor holds a charge until it is needed, our brains preserve moments in time, ready to influence our thoughts and actions. Scientists are continually pushing the boundaries of energy storage. Advances in nanotechnology and material science have led to capacitors with astonishingly high energy densities, hinting at the possibility of powering entire cities from devices small enough to fit in your hand. This ongoing quest to store power more efficiently underscores the importance of invisible energy reserves, both in our devices and in nature. As you settle into a state of calm, consider that beneath the surface of every object, every memory, there lies an invisible store of power waiting to be tapped, a quiet, persistent force that fuels the world, often without our ever noticing. The invisible storage of power is a tribute to the hidden energy that, while unseen, is the engine of innovation and the keeper of our collective memories. Level 66. The current that never stops. Electric current flows through our devices like a river of energy, connecting components and making the modern world function. But what happens when that current, once set in motion, seems to flow endlessly, defying the typical loss of energy we observe in everyday systems? This is the mystery behind the current that never stops, a paradox that challenges our understanding of how electrical energy moves and is conserved. In a perfect world, if there were no resistance, no friction, no external interference, an electric current could theoretically continue indefinitely. In superconductors, for example, electrons pair up into Cooper pairs and travel without resistance, allowing current to persist for incredibly long periods without any loss of energy. Superconductivity, observed at extremely low temperatures, reveals that under the right conditions, electrical energy can flow in a seemingly perpetual state. This phenomenon is not merely a laboratory curiosity. It has practical implications for power transmission, magnetic levitation, and even quantum computing. The idea that a current could keep flowing forever challenges our everyday experiences where energy is always lost as heat due to resistance. It raises fundamental questions about energy conservation and the nature of electrical circuits. The current that never stops is a testament to the elegance of nature's laws at their most refined. It suggests that when you remove all imperfections from a system, no friction, no resistance, the flow of energy becomes eternal. This idealized current contrasts sharply with the chaotic, dissipative currents we see in typical conductors, where microscopic interactions with atoms slow and eventually stop the flow. Imagine if we could harness this perpetual current on a large scale. It would revolutionize energy storage and transmission, leading to systems that operate with near-perfect efficiency. The possibilities for technological advancement are staggering. In a universe where currents can, under perfect conditions, flow forever, we are reminded of the potential for a future where energy is abundant and waste is minimized. As you relax and let your thoughts merge with the concept of endless energy, consider that the flow of electricity may be more than just a means to power our gadgets. It might be the very heartbeat of the cosmos, a current that, in its purest form, never stops. Level 67. The circuit of the universe. Imagine the entire cosmos as one gigantic electrical circuit, an endless network of currents flowing through the fabric of space. In our everyday experience, circuits power our devices, transmitting energy through conductive pathways. But what if the universe itself operated as a colossal circuit, where every star, planet, and particle is connected by invisible wires of energy? In this paradigm, cosmic events, from the birth of a star to the collision of galaxies, could be seen as moments in a grand electrical cycle. Just as electrons move through a circuit, carrying energy from one component to another, so might energy in the universe flow continuously through space. This idea suggests that the laws of electromagnetism that govern our small-scale gadgets might also scale up to the cosmic level. Every celestial body could act as a node, a capacitor storing energy, until the conditions are right for a surge, or a resistor that regulates the flow. Consider how lightning streaks across the sky, a brilliant, transient discharge that momentarily illuminates everything around it. Lightning is nature's own electrical circuit in action. Now imagine that on a grander scale. Vast cosmic currents energizing galaxies, powering supernovae, and even influencing the expansion of the universe. If the cosmos were a circuit, then dark energy or dark matter might be akin to unseen conductors and insulators that help shape the overall flow of energy. This model challenges our traditional view of the universe as a collection of isolated systems. Instead, it invites us to see it as a dynamic, interconnected network where energy circulates in an endless loop, sustaining life and fueling cosmic evolution. If every star and planet is a component in this circuit, then perhaps the behavior of one affects the others in subtle, measurable ways. An intricate dance of energy, where a fluctuation in one region can ripple across the vast expanse of space. The circuit of the universe paradox not only redefines our understanding of cosmic structure, but also suggests new ways to harness energy. Imagine if we could tap into these universal currents, drawing power from the natural flow of energy that permeates the cosmos. As you drift into a state of deep relaxation, ponder this idea. The universe may not be a random collection of matter, but a finely tuned circuit, where every particle plays a part in an endless, harmonious flow of energy. Level 68. The pulse of Aachen DC. Electricity comes in two distinct forms: alternating current, AC, and direct current, DC. These two systems, like night and day, each have their own rhythm and purpose. AC, with its oscillating flow, allows us to transform voltage and transmit power efficiently over long distances, while DC provides a steady, unwavering stream of energy vital for electronics. But what if the universe itself beats with the pulse of AC and DC, a dual rhythm that underlies all of reality? Consider the world around you. AC electricity creates the familiar hum of power lines and the periodic flicker of neon lights. Its alternating nature is dynamic and ever-changing, much like the cycles of day and night. In contrast, DC flows in one unidirectional path, a steady current that powers our devices with reliability and precision. These two modes of electricity mirror the dual nature of many phenomena in the cosmos, where change and consistency coexist. Imagine the cosmic scale. Stars and galaxies might be influenced by oscillatory forces similar to AC, while the steady pull of gravity and the unyielding march of time reflect a DC-like stability. Could it be that the universe is fundamentally powered by this duality? The pulse of AC and DC paradox invites us to contemplate that every force and every field might have its own natural frequency, its own rhythm of flow that collectively orchestrate the cosmic symphony. Moreover, technological advances increasingly blur the line between AC and DC. Modern power grids often convert one form to the other to optimize efficiency and performance. This interplay hints at a deeper connection between these two types of current, a unity where alternating and direct energy are merely different expressions of the same underlying power. As you relax and let your thoughts wander, consider that the hidden pulse of the universe may echo these two forms of electricity. The rhythmic oscillations of AC might represent the dynamic, ever-changing aspects of reality, while the steady, unidirectional flow of DC symbolizes the constant, enduring foundation upon which all existence is built. Perhaps, in this cosmic dance, the pulse of AC and DC is the very heartbeat of creation, a dual rhythm that not only powers our technology, but also underlies the grand, interconnected structure of the cosmos. Level 69. The magnetic field that shapes reality. Magnetic fields are invisible forces that govern a multitude of phenomena, from the simple behavior of a magnet on your refrigerator to the majestic spirals of distant galaxies. Imagine that these fields are not mere byproducts of charged particles, but the very architects of reality, guiding the formation and evolution of everything in the universe. Every magnet, no matter how small, creates an invisible field that exerts a force on other magnetic materials. On Earth, the planet's magnetic field not only guides compasses but also protects life by deflecting harmful solar radiation. In the vastness of space, magnetic fields sculpt the structure of galaxies, influence the formation of stars, and shape the swirling patterns of cosmic dust. The magnetic field that shapes reality paradox invites us to consider that these unseen forces may be more fundamental than we ever imagined. In the realm of physics, magnetic fields arise from the motion of electric charges. They interact with each other, creating complex patterns that can be both beautiful and chaotic. At the microscopic level, the magnetic moments of electrons combine to form the magnetism observed in everyday materials. But on a grand scale, entire galaxies are threaded with magnetic lines that twist and coil around spiral arms, hinting at a cosmic order hidden in plain sight. Could it be that magnetic fields are the scaffolding upon which the universe is built? Some theories suggest that these fields play a crucial role in the dynamics of dark matter and dark energy, mysterious components that make up the majority of the cosmos. The influence of magnetic fields may extend far beyond what we can directly measure, subtly guiding the behavior of particles, shaping cosmic structures, and even affecting the flow of time. As you let your mind relax, consider the possibility that the reality you experience is molded by these invisible forces. The magnetic field that shapes reality is a reminder that, while we may not see them, magnetic fields are constantly at work, binding, bending, and directing the flow of energy throughout the universe. They are the silent architects of creation, orchestrating a symphony of forces that shape everything from the tiniest atom to the grandest galaxy. Level 70. The induction that creates motion. Electromagnetic induction is one of the most fascinating phenomena in physics, a process where electricity is generated simply by changing magnetic fields. Imagine a world where a magnetic field doesn't just sit passively, but actively pulls and pushes, creating motion without any physical contact. In our daily lives, we see the practical side of induction in generators and transformers, yet the underlying concept goes far deeper. When a conductor moves through a magnetic field, or when the magnetic field around a stationary conductor changes, electrons begin to flow, creating an electric current. This transformation of magnetic energy into electrical energy happens seamlessly, almost like magic, and it's the engine behind much of modern technology. But what if induction is not just a tool for powering our homes? What if it reflects a universal principle? A force that can set objects into motion without the need for direct contact. Picture a scenario where invisible magnetic fields ripple through space, pulling objects along their unseen paths, much like the hidden forces that guide our destiny. This concept challenges our classical notion that a force must always be applied directly to move an object. Instead, induction shows us that change can be initiated remotely, with energy transferred through the void. At the heart of electromagnetic induction lies Faraday's law, which tells us that a change in magnetic flux through a circuit induces a voltage. In other words, the mere act of altering a magnetic field can breathe life into a circuit, setting electrons in motion. This phenomenon isn't limited to laboratory experiments. It is the foundation of everything from the flicker of a light bulb to the hum of massive power plants. In a cosmic sense, it suggests that the universe itself might be driven by similar principles, where shifting fields initiate grand cascades of motion that ripple through space and time. As you let these ideas settle, consider the beauty of a universe where motion is not solely the result of direct pushes and pulls, but can emerge from the invisible dance of magnetic fields. The induction that creates motion invites you to envision a realm where energy flows through space in unseen currents, transforming the mundane into the extraordinary, and where the potential for movement is limited only by our imagination. Level 71. The Whisper of Faraday. Faraday's discoveries revolutionized our understanding of electromagnetic phenomena. His groundbreaking experiments revealed that a changing magnetic field could induce an electric current in a nearby conductor, setting the stage for modern electrical engineering. But beyond the practical applications lies a more profound mystery. Could Faraday's law hold the key to unlocking limitless energy? Faraday's law tells us that the induced voltage in a circuit is proportional to the rate of change of the magnetic flux through it. In essence, even the slightest alteration in a magnetic field can whisper life into a dormant circuit, stirring electrons into motion. This whisper is subtle yet powerful, capable of driving enormous generators and powering cities. It's a quiet force that underpins much of our modern world. Yet, as we probe deeper into the nature of induction, we begin to wonder, could this principle be harnessed on a scale that defies our current technological limits? Imagine a device that captures the natural fluctuations of Earth's magnetic field, converting ambient energy into electricity without the need for fuel or external power. Such a breakthrough would revolutionize energy production, providing a constant, sustainable source of power. The whisper of Faraday paradox invites us to consider that the secret to infinite energy might lie not in complex nuclear reactions or exotic particles, but in the simple, elegant interactions of magnetic fields and conductors. Faraday's insights show us that even the faintest whisper from a changing field can awaken dormant electrons, sparking an endless chain of energy conversion. As you relax and listen to the quiet hum of the world around you, ponder the possibility that the natural rhythms of the earth could be the ultimate source of limitless power, a soft, persistent whisper waiting to be amplified by human ingenuity. Level 72. The shield of Lenz. When a magnetic field changes, it induces a current in a conductor, a phenomenon beautifully captured by Lenz's law. Lenz's law states that the direction of the induced current is such that it opposes the change in the magnetic field that produced it. In other words, nature creates a shield, a resistance against change, ensuring that any disturbance in the system is met with an opposing force. This shield is not a physical barrier, but an invisible reaction that preserves equilibrium. For example, when you move a magnet toward a coil, the coil generates a current that creates its own magnetic field, opposing the magnet's approach. This principle is fundamental not only to the functioning of generators and transformers, but also to the stability of many natural systems. Lenz's law ensures that energy is conserved and that changes do not occur without a compensatory response. The shield of Lenz paradox invites us to marvel at nature's inherent resistance to change, a built-in safeguard that balances the forces at work. It's as if the universe has an innate mechanism to preserve its current state, counteracting disturbances before they spiral out of control. This self-correcting behavior can be observed in many contexts, from the regulation of temperature in a room to the dynamic stability of planetary orbits. Yet, the implications extend further. Could this natural shielding be harnessed to create systems that resist unwanted changes? Imagine a technology that automatically counteracts energy loss or mechanical wear by generating forces that oppose degradation. Lenz's law, with its elegant simplicity, suggests that every action has an equal and opposite reaction, a principle that might one day be used to engineer more efficient machines or even to stabilize turbulent systems in nature. As you allow your thoughts to settle into calm, consider the protective power of nature, the unseen shield that keeps the universe in balance. The shield of Lenz reminds us that every change is met with resistance, a silent guardian that preserves the harmony of energy and motion, ensuring that the cosmos remains in a delicate equilibrium despite the constant flux of forces. Level 73. The equations that predict the unknown. Maxwell's equations are among the greatest achievements in physics, elegantly unifying electricity and magnetism into one coherent theory. These four equations not only describe the behavior of electric and magnetic fields, but also predict the existence of light as an electromagnetic wave. But what if their implications extend far beyond what we currently understand? What if these equations hold secrets about phenomena we have yet to discover? Maxwell's equations reveal that a changing magnetic field generates an electric field and vice versa. This interplay gives rise to electromagnetic waves that travel at the speed of light. When you see a beam of light, you're witnessing the manifestation of these fundamental forces interacting in perfect harmony. Yet, these same equations hint at deeper connections. They imply that space itself can support oscillations and waves, suggesting that our universe might be an intricate tapestry woven from fields and energies we have only begun to explore. Imagine a world where these equations could predict not only the behavior of light, but also the emergence of unknown forces. In extreme conditions, such as near black holes or during the early moments of the Big Bang, Maxwell's equations might take on new forms, revealing hidden dynamics that could explain the mysteries of dark matter or dark energy. These unknown aspects could be the keys to understanding how energy and matter interact on cosmic scales, pushing the boundaries of our conventional models. The equations that predict the unknown invite you to look beyond the visible spectrum, to consider that the familiar laws governing electricity and magnetism are merely a glimpse into a far more complex realm. As you drift into sleep, let your mind wander through the endless possibilities these equations might unlock. They serve as a reminder that even the most established scientific principles can hide profound secrets, waiting to be uncovered by those who dare to question the limits of knowledge. Level 74. The waves that see everything. Electromagnetic waves are not just carriers of light and radio signals. They are the messengers of the universe, permeating every corner of space and time. These waves travel silently, invisibly, yet they carry vast amounts of information about the cosmos. From the rhythmic pulse of a radio broadcast to the intricate patterns of light that form a star's spectrum, electromagnetic waves reveal the hidden workings of nature. Imagine a world where every whisper of electromagnetic energy is like a silent observer, capturing and transmitting information from every event occurring in the universe. Even as you sleep, your body is bathed in these waves, signals from distant galaxies, the hum of our planet's magnetic field, and even the subtle glow of cosmic microwave background radiation that dates back to the birth of the universe. These waves are the eyes of the cosmos, constantly seeing everything, yet their gaze remains unseen to us. The waves that see everything. Paradox challenges us to consider that reality is filled with invisible currents that continuously record the history and evolution of the universe. Every fluctuation in a magnetic field, every vibration in the air, contributes to a vast, interconnected network of information. This network not only carries data about the physical world, but might also influence the behavior of matter at a fundamental level. As you relax, imagine the electromagnetic waves around you as quiet sentinels, always watching, always recording, silently shaping the fabric of existence. Their omnipresence is a testament to the subtle complexity of nature, a reminder that even when we close our eyes, the universe continues its ceaseless observation. Level 75. The spectrum that surrounds you, light, as we perceive it, is only a small fragment of the electromagnetic spectrum. Beyond the colors visible to our eyes lie realms of infrared, ultraviolet, X-rays, and even more exotic frequencies that pass through our bodies and fill the cosmos. The spectrum that surrounds you. Paradox invites you to explore the idea that what we see is just a fraction of the true richness of light, a hidden rainbow of energy that remains unseen yet profoundly influences our world. Every object emits radiation at various frequencies, a natural signature that defines its temperature, composition, and even its age. Infrared light warms our skin, ultraviolet rays can trigger chemical reactions, and X-rays reveal the hidden structure of our bones. These forms of light exist all around us, silently interacting with matter, driving the processes of life, and even shaping the evolution of the universe. Yet, they are invisible to our naked eyes. This paradox challenges the notion that our perception of light is complete. It asks us to consider the possibility that the universe is bathed in a myriad of wavelengths, each carrying unique information about the cosmos. The spectrum is not a simple line from red to violet. It is an expansive continuum where every segment reveals a different aspect of reality. As technology advances, we continue to develop instruments that peel back the layers of this spectrum, uncovering phenomena that once belonged to the realm of pure theory. Imagine that as you sleep, your body is not only receiving visible light, but is also subtly influenced by the hidden energies of infrared and ultraviolet waves. These invisible frequencies might be silently communicating messages across the cosmos, signals that shape weather patterns, influence biological rhythms, and even guide the evolution of stars. The spectrum that surrounds you serves as a reminder that our sensory experience is limited and that the true nature of light is far more complex and wondrous than we can perceive. Let your mind drift into the thought that beyond the colors you see, an entire universe of light is continuously at work, illuminating the hidden corners of existence in ways that defy imagination. Level 76. The light that acts like water. Light is known to exhibit a dual personality. It flows like a continuous wave and yet strikes like a discrete particle. This puzzling behavior challenges our classical understanding of physics. Imagine watching ripples on a pond. They spread smoothly across the water, their crests and troughs merging into one another. Now, picture that same water suddenly breaking into droplets, each one distinct and separate. In the world of light, this is precisely what occurs. In some experiments, light behaves as a wave, creating interference patterns and diffracting around obstacles. In others, it impacts a surface in individual packets called photons. How can something be both a wave and a particle? This conundrum lies at the heart of quantum mechanics and is known as wave-particle duality. When light passes through a narrow slit, it produces an interference pattern, clear evidence of its wave nature. Yet, when detectors are placed to measure the light's impact, it registers as individual particles. It is as if light is playing both roles simultaneously, defying a straightforward categorization. Some physicists suggest that light, along with all quantum objects, exists in a state of probability until it is observed. In this view, light is neither purely a wave nor purely a particle. It is a combination of both, governed by the mathematical framework of quantum theory. The act of measurement forces it to choose one behavior over the other. This mysterious process is still not fully understood, and it challenges our intuition about the nature of reality. Imagine a world where water behaved in such a dual manner, flowing like a liquid, and yet impacting surfaces as discrete droplets, with unique energy levels. Such a phenomenon would completely upend our understanding of fluid dynamics. In a similar way, the dual nature of light forces us to rethink the fundamental laws that govern energy, matter, and their interactions. As you relax and let your thoughts wander, consider that light's ability to act like water, flowing gently, one moment and striking powerfully the next, may be a metaphor for the universe itself. In a cosmos filled with uncertainties and probabilities, light embodies the delicate balance between continuity and discreteness, a reminder that nature's rules are often more intricate and mysterious than they appear. Level 77. The reflection of the infinite. A mirror is a window into our world, a perfect reflection of reality. But what if a mirror revealed more than just your image? Imagine a mirror that doesn't merely replicate what stands before it, but instead presents an inverted, infinite echo, a world that stretches into the unknown. This is the reflection of the infinite paradox, where the simple act of looking into a mirror becomes a journey into boundless mystery. When you gaze into a mirror, you expect to see yourself, unchanged and familiar. Yet a mirror also reverses, swapping left and right, creating an altered perspective of reality. Now amplify that effect until the mirror seems to extend beyond its physical limits, reflecting not just your image but an infinite cascade of echoes, each one slightly fainter yet stretching into eternity. It's as if you are peering into a universe within a universe where every reflection holds the secret of endless repetition. This paradox invites us to question the nature of perception and the limits of our reality. Could it be that what we see in a mirror is not the entire truth, but a hint of a deeper, infinite structure of existence? Perhaps each reflection is a portal, a fragment of a larger cosmic tapestry, where space, time, and identity are endlessly reproduced. The mirror's reversal challenges our conventional sense of direction and order, hinting that reality might be more fluid and boundless than we think. In some interpretations of quantum mechanics, particles can exist in multiple states simultaneously, until observed. Similarly, the infinite reflection might symbolize the idea that every moment in life is a part of an endless chain, each echoing the one before it, yet subtly different. This continuous reflection could be seen as a metaphor for the infinite potential that lies hidden within every individual, a reminder that our existence may extend far beyond the limits of what we perceive. Allow your mind to drift into the possibility that the mirror in front of you is not just a surface, but a gateway to an infinite world of reflections that challenges the boundaries of space and time. Level 78. The Bending of Reality. When you observe light passing from one medium to another, such as air into water, it bends, a phenomenon known as refraction. But what if this bending wasn't confined to light alone? What if it could extend to bending time itself, reshaping the fabric of reality in ways we have yet to imagine? This is the bending of reality paradox, a concept that challenges our understanding of both optics and the nature of space-time. Refraction is a familiar process. A straw in a glass of water appears broken or bent at the surface, a simple trick of light. Yet, this seemingly mundane occurrence opens a window into deeper mysteries. In the world of physics, light does not travel in a straight line when it moves through different media. It curves, its speed altered by the properties of the medium. This principle is at the heart of lenses, optical instruments, and even the natural focusing of sunlight. Now, extrapolate this idea to the cosmic scale. Einstein's general theory of relativity tells us that gravity bends the path of light, curving space-time around massive objects. But what if refraction isn't limited to light alone? What if, in extreme conditions, the very fabric of space-time could be refracted, bent and twisted like light through water? Imagine a region of space where time stretches and warps as if passing through a cosmic lens, creating pockets where the flow of time is radically different. This concept suggests that reality might be far more flexible than we assume. The bending of reality paradox invites us to consider that space, time, and light are intertwined in an intricate dance, where the laws of physics are not rigid but adaptable. Under certain circumstances, the interplay between gravitational forces and the properties of space could lead to phenomena that appear to bend time, altering our perception of cause and effect. As you relax, let your thoughts flow into the possibility that the universe is not fixed, but malleable, capable of bending and shifting like a liquid. The bending of reality is a reminder that even the most familiar phenomena may hide deeper, more transformative secrets that could one day reshape our understanding of time, space, and existence itself. Level 79. The Secret of Diffraction. Diffraction is a phenomenon where light bends around obstacles or passes through narrow openings, producing patterns of light and dark fringes that reveal hidden details of the wave's nature. Imagine shining a beam of light through a tiny slit. Instead of simply forming a sharp line on a screen, the light spreads out, creating an intricate pattern that seems almost magical. This bending of light is not just a quirk of optics, it's a window into the dual nature of light itself. At its core, diffraction exposes the wave-like behavior of light. While we often think of light as rays traveling in straight lines, diffraction reminds us that light is also a wave, capable of spreading, interfering, and interacting with its environment in complex ways. When light encounters a small aperture or an edge, it sneaks around the barrier, much like a whisper that travels softly around a corner in the dead of night. This gentle bending reveals information about the size and shape of the opening, and it's the very principle behind technologies such as diffraction gratings, which are used to disperse light into its component colors. Moreover, diffraction isn't limited to light alone. It occurs with all types of waves: sound, water, and even matter waves at the quantum level. The patterns created by diffraction can tell us much about the object causing the disturbance. In advanced scientific experiments, Researchers use diffraction to probe the atomic structure of materials, revealing the hidden order within crystals. Such techniques have been instrumental in fields ranging from materials science to biology. This phenomenon challenges our everyday intuition. We expect objects to block light completely, yet diffraction shows that even an obstacle can only partially impede a wave's progress. Instead, light finds its way through tiny spaces and around edges, creating complex interference patterns that are both beautiful and informative. The secret of diffraction, then, is a reminder that the natural world is full of subtle details, whispers of information hidden within the behavior of waves. As you relax, imagine these delicate patterns spreading across the darkness, a silent ballet of light that reveals the hidden structure of the universe. Level 80. The Dance of Interference. Interference is the mesmerizing phenomenon that occurs when waves meet, sometimes canceling each other out, other times amplifying into brilliant crescendos. Think of two pebbles dropped into a pond, each generating ripples that merge, creating complex patterns of crest and trough. In the realm of light, interference produces striking patterns of bright and dark bands, a clear signature of its wave-like behavior. This dance of interference is not merely a physical occurrence. It offers a metaphor for the interplay of ideas and energies. When two coherent light waves interact, they can either reinforce each other, producing areas of intense brightness, or they can cancel out, leaving shadows of silence. Such interplay is governed by the principle of superposition, where the resultant wave is simply the sum of the individual waves. Imagine if our thoughts worked in the same way, if ideas could amplify or cancel each other out based on their harmony or discord. In the laboratory, interference is a powerful tool. It is used in devices like interferometers, which measure incredibly small distances by analyzing the patterns of light interference. These instruments have been crucial in discovering gravitational waves, confirming that even the most subtle ripples in space-time can be detected when the conditions are right. The delicate balance of constructive and destructive interference not only creates beauty in optical experiments, but also reveals the hidden structure of reality. As you allow your mind to wander, consider that the dance of interference might be a fundamental principle that extends beyond physics. Perhaps the interactions between our thoughts, emotions, and experiences also follow a pattern of interference, where harmony creates clarity and discord leads to confusion. The dance of interference reminds us that every encounter, every merging of ideas, contributes to a larger, ever-changing pattern that shapes our reality. Let this idea lull you into a state of reflective calm, where even the chaotic moments of life blend into a harmonious rhythm. Level 81. The Force Fields of the Universe. Force fields are invisible, yet they govern every interaction in the cosmos. Whether it's the gravitational field that binds planets and stars, the electric field that influences charged particles, or the magnetic field that shapes entire galaxies, these unseen forces create a framework for the universe. The force fields of the universe paradox invites us to look beyond visible matter and see the intricate, invisible web of fields that orchestrate all cosmic events. Every charged particle generates an electric field extending outward into space, affecting other charges even at a distance. Similarly, magnetic fields born from the motion of electrons wrap around objects, guiding the trajectories of everything, from compass needles to solar winds. These fields are not static. They interact, combine, and change continuously, shaping the environment on both microscopic and macroscopic scales. In the vacuum of space, where matter is sparse, these fields still exist, silently influencing the motion of galaxies and the evolution of stars. Imagine the universe as a vast, interconnected grid of force fields, where every object is both a source and a receiver of invisible energy. This network not only dictates the behavior of matter, but also influences the flow of energy and information across the cosmos. From the spiraling arms of distant galaxies to the subtle oscillations of quantum particles, force fields are the hidden architects of reality. They provide the structure within which everything happens, yet they remain unseen, operating in a realm beyond our direct perception. As you relax, let your thoughts drift into this invisible world, a place where every interaction, every collision of particles is orchestrated by an intricate web of fields. The force fields of the universe remind us that what we see is only a fraction of reality. Beneath the surface, an elaborate dance of forces is continuously at work, crafting the structure and behavior of the cosmos in ways that inspire both wonder and humility. Level 82. The glow of the void. Even in what we call total darkness, the universe is never truly black. There is a faint, ghostly luminescence that emanates from the vacuum of space, a subtle glow produced by particles flickering in and out of existence. This phenomenon, known as the glow of the void, challenges our perception of emptiness. What we consider nothing is in fact teeming with activity. In quantum field theory, empty space is not an inert void, but a seething background, where virtual particles constantly pop into and out of existence. These ephemeral particles, though short-lived, radiate tiny amounts of energy, creating a gentle, pervasive glow. It is as if the void itself is alive, quietly humming with potential energy that never fully dissipates. This mysterious radiance is not visible to the naked eye but can be detected with sensitive instruments, offering a glimpse into the hidden dynamics of the cosmos. Imagine drifting in the vast emptiness of space, where even the darkness is filled with a soft, radiant glow. It is a reminder that the universe is never truly empty. There is always energy, always movement at a microscopic level. This subtle luminescence hints at the intricate interplay of forces that govern all of existence, suggesting that even in the absence of matter, the cosmos vibrates with a silent symphony of energy. The glow of the void invites us to rethink the concept of nothingness. Instead of being a barren, lifeless expanse, empty space may be a dynamic arena where energy, matter, and force are in constant flux. This idea has profound implications. If the void itself radiates energy, could we one day harness this hidden power? Or might it be the key to understanding the fabric of space-time itself? As you relax and drift off, let your mind wander through the dark expanse of the universe. Picture the silent glow of the void, a gentle light that reminds us even the deepest darkness is filled with unseen activity. This is the cosmic heartbeat, a soft, persistent pulse that underscores the fact that in the universe, nothing is ever truly empty. Level 83. The building blocks of everything. When you look around, you see objects that appear solid and impenetrable. Yet at the most fundamental level, they are composed mostly of empty space. Atoms, the building blocks of everything, are astonishingly hollow, tiny nuclei surrounded by vast regions where nothing seems to exist. This paradox, known as the building blocks of everything, challenges our intuitive understanding of matter. In an atom, protons and neutrons are packed tightly in a central nucleus, while electrons exist in probabilistic clouds that occupy most of the atomic volume. Despite the common perception of solidity, the atom is more like a miniature solar system where the space between the nucleus and the electron cloud is overwhelmingly empty. This realization is both humbling and mind-expanding. The matter that makes up your body, the stars, and the universe at large is predominantly empty space. Yet this emptiness is far from meaningless. The void within an atom is a canvas upon which the forces of nature operate. Electromagnetic fields, quantum fluctuations, and the strong nuclear force all interact within these gaps, determining the properties and behavior of matter. The paradox here is that even though atoms are mostly empty, they somehow give rise to the solidity and structure that we observe in everyday life. It is as if the nothingness inside atoms is what allows them to interact in such complex and stable ways. The building blocks of everything forces us to reconsider what it means to be solid. Perhaps the solidity we experience is not due to the presence of matter in the traditional sense, but rather the interplay of forces within vast amounts of empty space. This concept opens up a fascinating perspective on how matter is formed and how the universe is structured. As you drift off into relaxation, imagine the hidden emptiness within every object, a delicate balance of nothingness and force that creates the world you see. Every atom is a marvel, a tiny testament to the complexity of nature, where the absence of substance is as critical as its presence. Level 84. The particles that aren't particles. Our classical view of matter paints a picture of tiny, solid particles that make up everything around us. However, quantum physics has revealed that these particles are not as solid as once thought. In fact, they behave more like vibrating waves of energy, blurring the lines between matter and energy. This is the essence of the particles that aren't particles paradox, a concept that challenges our conventional understanding of what particles truly are. Electrons, protons, and neutrons, which we once imagined as discrete, hard objects, are now known to exhibit dual characteristics. They can behave like particles when measured, but also display wave-like properties, spreading out and interfering with themselves. In this realm, particles are best described by probabilities and wave functions, existing in multiple states until observed. This quantum behavior is not limited to electrons. Even light, traditionally seen as a wave, also comes in quantized packets called photons. This paradox suggests that what we perceive as matter may be nothing more than a manifestation of energy vibrating at specific frequencies. In this view, particles are not fixed entities but dynamic, fluctuating phenomena that exist only when observed. The boundary between what is real and what is a mere probability becomes blurred, leading us to question the very nature of reality. If particles are essentially waves of energy, then the solidity and stability of matter are emergent properties, consequences of how these energy waves interact, collapse, and stabilize. It is the interplay of these waves that gives rise to the tangible world, a world where objects seem solid even though their true nature is fluid and dynamic. As you let your thoughts wander into the quantum realm, consider that the very blocks of reality are not rigid, but rather an intricate dance of energy and probability. The particles that aren't particles challenge you to embrace the uncertainty and fluidity of the universe, a reminder that our perceptions may only scratch the surface of a deeper, more complex reality. Level 85. The electrons' hidden path electrons are the fundamental carriers of electricity and one of the basic building blocks of matter. Yet, despite their critical role in everything from powering our devices to forming the very structure of atoms, electrons behave in ways that remain shrouded in mystery. They move in unpredictable, seemingly random patterns, a hidden path that defies classical expectations. In quantum mechanics, electrons are not pinned down to a precise trajectory. Instead, they exist as probability clouds, described by wave functions that give only the likelihood of an electron being found in a certain place when measured. This inherent uncertainty is a core aspect of quantum physics, encapsulated by Heisenberg's uncertainty principle, which tells us that the more precisely we know an electron's position, the less precisely we can know its momentum, and vice versa. The electron's hidden path paradox challenges us to accept that, on a microscopic scale, the behavior of matter is not governed by definite trajectories, but by probabilities. When you observe an electron, you get a snapshot of where it might be, but that is only one possible outcome among many. In between observations, the electron seems to follow a path that we cannot predict. Its journey is as mysterious as it is fundamental. This hidden path is not just an abstract concept, it has real implications for technology. In semiconductors, for example, the behavior of electrons determines the performance of microchips and transistors. Yet engineers must design devices while accounting for the inherent uncertainty of electron motion. The unpredictable nature of electrons is what makes quantum computing possible, where information is processed in ways that defy classical logic. It also forms the basis for phenomena like superconductivity, where electrons move in coordinated pairs without resistance. As you let your mind relax, imagine the intricate dance of electrons, each one following a hidden path, a journey defined by chance and probability rather than a straight, predictable line. Their elusive behavior is a reminder that at the heart of matter, the rules of the universe are not as rigid as they seem, but rather a fluid interplay of possibilities waiting to be discovered. Level 86. The light that frees electrons. The photoelectric effect revolutionized our understanding of light and matter by demonstrating that light possesses a dual nature. It behaves both as a continuous wave and as discrete packets of energy, called photons. When light strikes a material, it can free electrons from that material, a process that depends on the energy of the photons. This phenomenon, where light liberates electrons, is the basis for countless technologies, from solar panels to photodetectors. Yet, the fact that light can simultaneously behave as a wave and as a particle presents a profound paradox. How can one entity exhibit two seemingly contradictory natures? In classical physics, waves and particles were seen as distinct. Waves, like water ripples, are continuous and spread out over space. Particles, on the other hand, are discrete, localized points of matter. The photoelectric effect, however, forced scientists to confront the reality that light does not fit neatly into either category. When light of a certain frequency hits a metal surface, electrons are ejected. This can only be explained if light delivers energy in small, quantized packets. Yet, when unobserved, light behaves like a wave, spreading out and interfering with itself in patterns that only waves can create. This duality is at the heart of quantum mechanics, suggesting that particles, including photons, exist in a state of probability until measured. The light that frees electrons paradox challenges us to rethink our classical notions of matter and energy. It forces us to accept that the universe at its most fundamental level is governed by principles that defy everyday logic. In the act of freeing electrons, light bridges the gap between the wave and particle worlds, creating a phenomenon that is both elegant and bewildering. Allow your thoughts to drift with the idea that light, the very medium of vision and energy, is far more complex than it appears, a mysterious force that both flows and strikes, liberating the building blocks of matter and reshaping our understanding of reality. Level 87. The shapes that govern reality. Geometry isn't merely a branch of mathematics, it's a language that describes the very structure of the universe. The shapes that govern reality paradox challenges us to consider that the hidden geometry of space might be the blueprint on which the cosmos is built. From the simple curves of a circle to the intricate patterns of fractals, shapes appear in nature with an uncanny regularity, guiding everything from the orbit of planets to the spiral of galaxies. At the atomic level, the arrangement of electrons around a nucleus creates patterns that determine chemical properties. On a larger scale, the curvature of space-time described by general relativity is itself a geometric phenomenon. Gravity is the manifestation of how mass bends the fabric of space. Even the chaotic formations in turbulent fluids reveal an underlying order that mathematics can describe with elegant precision. This suggests that geometry is not just a tool for measurement but a fundamental aspect of existence. Consider the possibility that the universe is built on a deeper, hidden pattern, a geometric code that governs not only the visible arrangement of matter, but also the laws of physics themselves. This idea finds resonance in string theory, where the vibrations of tiny, one-dimensional strings give rise to the particles and forces we observe, and the shapes of extra dimensions dictate the properties of these particles. The paradox here is that what we perceive as random or chaotic might be the result of a complex, underlying geometry that we have yet to fully decipher. As you relax, imagine that every structure in the universe, every galaxy, every star, even every molecule, is governed by a set of invisible, intricate patterns. These shapes may determine the very behavior of reality, directing the flow of energy, the force of gravity, and the interaction of matter. The shapes that govern reality invite you to see the world not as a collection of isolated objects, but as an interconnected tapestry woven from the threads of geometry, a cosmic design that holds the secrets of existence within its elegant curves and patterns. Level 88. The fractals of space and time. Fractals are patterns that repeat at every scale, a concept that transcends mathematics and appears throughout nature. Imagine zooming into a coastline or a snowflake. No matter how much you magnify, you see similar patterns repeating over and over. This is the essence of fractals, and it poses a fascinating question. Could the very fabric of space and time be built on such infinitely repeating structures? In our everyday lives, we perceive space as continuous and smooth, and time as a linear progression. However, when we delve into the microscopic or cosmic scales, the universe reveals a hidden fractal nature. At the quantum level, particles and fields display patterns that hint at self-similarity, while on astronomical scales, the distribution of galaxies and cosmic web structures seems to follow fractal-like distributions. These repeating patterns suggest that chaos and order are not opposites, but are interwoven in an endless tapestry. The fractals of space and time paradox invites us to consider that the universe might be organized in layers upon layers of repeating structures. These fractal patterns could be the hidden blueprint of the cosmos, where the same rules apply whether you're looking at a single atom or a vast galaxy cluster. This idea not only challenges our understanding of scale, but also hints at a profound unity in nature, where every part of the universe is connected by the same underlying geometry. If space and time are indeed fractal, then every fluctuation, every ripple in the fabric of reality, might mirror a pattern that is repeated infinitely. This could mean that the dynamics of the universe, its expansion, its gravitational interactions, and even the flow of time itself are governed by these recurring self-similar rules. Such a perspective might ultimately bridge the gap between the seemingly chaotic microcosm of quantum mechanics and the grand order of cosmic structure, revealing that randomness is only an illusion masking a deeper, intricate order. As you let your mind wander into the night, consider that you are part of a vast fractal pattern, a piece of an endless cosmic puzzle that repeats itself at every scale. The fractals of space and time are not just mathematical curiosities. They are the hidden architecture of the universe, whispering secrets about how everything is connected in an eternal, repeating dance. Level 89. The chaos that creates order. EA. First glance, chaos appears as disorder and randomness, a tumultuous state with no discernible pattern. Yet, beneath the surface of what seems unpredictable, hidden rules and underlying structures often emerge, orchestrating a complex symphony of order. This is the essence of the chaos that creates order paradox, a concept that challenges the conventional idea that chaos is simply the absence of order. In many natural systems, from weather patterns to the movement of celestial bodies, chaos plays a crucial role. Small variations in initial conditions can lead to vastly different outcomes, a phenomenon famously described as the butterfly effect. But rather than being a sign of mere disorder, chaos often gives rise to intricate patterns and stable structures. For instance, turbulent flows in fluids, though seemingly random, can create coherent vortices and patterns that persist over time. Similarly, chaotic dynamics in population growth or financial markets sometimes lead to unexpected regularities, revealing that order can arise from disorder. The chaos that creates order paradox compels us to see that randomness and structure are not mutually exclusive. In the microscopic world, quantum fluctuations may seem random, yet they form the basis for the stability of atoms and molecules. On a cosmic scale, the erratic motions of stars in a galaxy eventually settle into well-defined orbits and patterns dictated by gravitational forces. These examples hint that chaos is a fertile ground for order, a canvas on which nature paints its most intricate and beautiful designs. As you drift toward sleep, imagine the universe as a vast, dynamic interplay of chaos and order, a place where every unpredictable moment is part of a larger, hidden design. The seemingly random behavior of particles and galaxies might actually be the result of underlying principles that govern the emergence of structure. In this light, chaos is not simply a state of disarray. It is the very process through which the cosmos organizes itself, creating the stable, ordered world we experience. Let this idea resonate as you relax. Within the unpredictable, chaotic pulse of the universe, there lies a deep inherent order waiting to be discovered, a reminder that even the wildest randomness may be the source of life's most profound harmony. Level 90. The clock that runs differently. Time, as we perceive it, ticks along uniformly, a steady beat that structures our lives. Yet Einstein's theory of special relativity revealed that time is not absolute. It is elastic, bending under the influence of speed. This is the clock that runs differently. Paradox, where time itself becomes a variable, slowing down or speeding up depending on how fast you move. Imagine two identical clocks. One remains on Earth while the other embarks on a high-speed journey through space. Upon reunion, the traveling clock shows less elapsed time than the stationary one, as if time itself had slowed down during the journey. This phenomenon, known as time dilation, has been confirmed by experiments with fast-moving particles and precision atomic clocks. It challenges our very notion of time as a constant, suggesting that time is relative, a fluid concept that changes with speed and gravity. Now, envision a world where time does not pass uniformly for everyone. In such a universe, our experience of the present, past, and future is not fixed, but varies with our motion and location. High-speed travel might allow some to experience time more slowly, while others age faster. This bending of time implies that the future can be reached in less time than the present suggests, and that our linear perception of time is merely an artifact of our everyday experiences. The clock that runs differently. Paradox pushes us to imagine that time, like a flexible clock, can be stretched and compressed. This elasticity of time hints at a deeper reality where the boundaries between moments are not rigid but fluid, where events can overlap and the sequence of cause and effect might blur. If our clocks truly run differently depending on our state of motion, then our perception of time is not a universal constant, but a personalized experience, influenced by the very conditions of our existence. As you drift into relaxation, let your thoughts wander to the possibility that time is not the fixed, unyielding march we assume it to be, but a malleable dimension that bends and flexes like a rubber band. The clock that runs differently reminds us that the flow of time is as mysterious as it is profound, challenging our most fundamental assumptions and inviting us to explore a universe where every moment is both fleeting and eternal. Level 91. The energy that becomes matter. Einstein's famous equation, E=mc2, is more than a mathematical relationship. It is a profound key that unlocks the very nature of existence. This equation tells us that energy and mass are two sides of the same coin. Energy can be transformed into mass, and mass can be converted back into energy. Imagine, for instance, the intense energy produced in nuclear reactions where small amounts of mass vanish, releasing enormous amounts of energy. This isn't just a curiosity of physics. It is the very process that powers our stars and creates the elements that build our world. In every atom, the mass of the nucleus is a measure of the energy bound within it. The energy stored in these tiny particles is what gives matter its substance. But if energy can become matter, then in principle matter can emerge from pure energy, a concept that upends our classical view of a solid, unchanging universe. The energy that becomes matter paradox invites us to imagine a time when the cosmos was a seething, formless pool of energy, which gradually coalesced into the structured, material universe we know today. This conversion is not just a theoretical notion. It has practical applications too. Nuclear reactors and atomic bombs operate on this principle, releasing energy stored in mass to perform work or create astonishing explosions. On a cosmic scale, the fusion processes in stars, convert mass into energy, sustaining the brilliant light and heat that make life possible on planets like Earth. Every ray of sunlight is a testament to this incredible transformation. Yet, the mystery lingers. If energy is ever present and can transform into matter, where does it all come from? The Big Bang is thought to have been the moment when a vast amount of energy condensed into particles, forming the building blocks of the universe. The seamless conversion between energy and mass suggests that everything around us, the air we breathe, the ground we walk on, the stars above, is simply manifestations of energy in different forms. As you drift into a deep, reflective state, ponder the idea that every object, every living thing, is a temporary arrangement of energy that can be reshaped at any moment. The energy that becomes matter is not just a law of physics. It is a poetic reminder that our entire existence is an ever-changing interplay of energy, continuously transforming and yet forever conserved. Level 92, the gravity that warps time. Gravity is the force that binds the cosmos, yet its influence extends far beyond mere attraction. Einstein's theory of general relativity revealed that massive objects do not simply pull on one another, they warp the very fabric of space-time. This warping causes time to slow down in strong gravitational fields, effectively bending the flow of time itself. Consider a clock near a massive object. Its tick-tock is noticeably slower compared to one in the emptiness of space. The gravity that warps time paradox invites us to explore a universe where time is as malleable as clay. In the presence of immense gravitational forces, such as near black holes or neutron stars, time dilates dramatically. This means that events occurring close to these objects could unfold at a glacial pace relative to the rest of the universe. The effect is so profound that if you were to venture close to a black hole and then return to Earth, you might find that many more years have passed for everyone else than for you, a phenomenon famously illustrated in the twin paradox. Beyond the fascinating time dilation effects, this warping of time challenges our conventional notion of past, present, and future. Gravity might not just slow time, it could also intertwine different moments, merging the boundaries between what we consider now and what we consider then. In such a universe, time may be less a linear progression and more a vast, malleable continuum that bends under the weight of mass and energy. Imagine the possibility that gravity's ability to warp time could be harnessed. Could we someday use intense gravitational fields to slow down time for specific purposes or even to glimpse into the future? As you relax, reflect on the fact that every massive object, every planet, star, and galaxy is not only pulling on matter but is also gently tugging on time itself, shaping the rhythm of the cosmos in subtle, profound ways. The gravity that warps time paradox challenges us to see time not as an unyielding clock, but as a flexible, dynamic component of the universe, one that is continuously molded by the presence of mass. Level 93, the discreteness of reality. In our everyday experience, the world appears continuous, a smooth expanse where distances, speeds, and even time flow without interruption. Yet, at the most fundamental level, reality might be composed of tiny, indivisible chunks, or quanta, that defy the illusion of continuity. The discreteness of reality paradox suggests that everything we observe is quantized, existing in fixed, discrete units that challenge our classical understanding of a smooth, flowing universe. Quantum mechanics reveals that properties like energy, momentum, and even angular momentum come in quantized amounts. Electrons orbit an atom in specific fixed energy levels rather than a continuous range. This means that the atomic world is not a blurry continuum, but a series of distinct quantifiable states. The paradox here is that while our senses perceive a seamless reality, the underlying structure is remarkably granular. Imagine viewing a digital image. Up close, you can see individual pixels, tiny dots that combine to create a smooth picture from a distance. In a similar way, the universe might be made up of pixels of space, time, and energy. These quanta are so minuscule that they escape direct observation, yet they form the foundation of everything we know. The idea that reality is discrete, rather than continuous, challenges the classical notion of infinite divisibility, suggesting that there is a smallest possible unit, a fundamental grain of existence beyond which nothing can be subdivided. The implications of this paradox are profound. If space, time, and energy are quantized, then the universe is more like a vast mosaic than a flowing river. This perspective could explain why certain processes, such as the emission of light or the interactions between particles, occur in sudden quantized bursts rather than smooth transitions. It also raises questions about the nature of measurement and observation. If the universe is fundamentally discrete, then our instruments might only be sampling a fraction of its true complexity. As you drift into a state of calm, let your thoughts explore the possibility that beneath the smooth veneer of everyday life lies a world of tiny, indivisible units. The discreteness of reality paradox invites you to consider that every moment, every distance, every amount of energy is a fixed step in a grand cosmic staircase, a reminder that the fabric of existence might be woven from countless, distinct threads rather than an unbroken continuum. Level 94. The duality of everything. A cornerstone of modern physics is the realization that particles are not just particles, and waves are not just waves. Each exhibits properties of the other in a phenomenon known as wave-particle duality. Consider light. Sometimes it behaves as a continuous wave, bending, interfering, and diffracting in elegant patterns. Other times, it strikes as discrete packets of energy called photons. But which is real? In our everyday experience, we classify objects as either particles or waves. Yet, at the quantum level, these categories dissolve into one another, challenging the very nature of reality. The duality of everything suggests that the universe does not adhere strictly to our classical notions. When electrons orbit an atomic nucleus, they do not follow fixed paths like planets around the sun. Rather, they exist in clouds of probability, both particle-like and wave-like until measured. This paradox invites us to question our perception. Is the physical world a collection of solid, well-defined objects, or is it a fluid interplay of possibilities? The answer is not clear-cut. Rather than being mutually exclusive, the particle and wave descriptions are complementary, offering two ways of understanding the same underlying phenomena. This duality is more than an abstract concept. It has practical implications that have transformed technology. The photoelectric effect, which earned Einstein his Nobel Prize, is a prime example. Light must be understood as both a wave to explain interference patterns and as a particle to account for the energy required to free electrons from metal surfaces. Such dual behavior is at the heart of modern electronics and quantum computing, where the precise manipulation of these properties drives innovation. Moreover, the duality of everything challenges us to reconsider what is real. When a particle is observed, its wave function collapses into a definite state, but before measurement, it exists in a superposition of states, an amalgam of every possible outcome. Is reality then something that exists independently, or is it co-created by our observations? This philosophical and scientific puzzle forces us to acknowledge that the true nature of the universe might be far more complex than our everyday experience suggests. As you drift into a state of relaxation, let your mind contemplate this profound duality, a reminder that every flash of light and every whisper of a particle embodies the enigmatic dance of existence, where nothing is as simple as it appears and the boundaries between matter and energy, wave and particle, are forever intertwined. Level. Here, the uncertainty of the smallest things. At the heart of quantum mechanics lies Heisenberg's uncertainty principle, a principle that upends our conventional expectations by stating that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This fundamental uncertainty isn't a flaw in measurement, it is an intrinsic property of nature. When we peer into the subatomic world, we encounter particles that do not possess definitive positions or speeds until observed. Imagine trying to track a tiny electron moving within an atom. Instead of following a clear trajectory, it exists as a cloud of probability, its position spread out over space. This inherent fuzziness means that, no matter how sophisticated our instruments, there's always an element of uncertainty, a limit beyond which nature refuses to divulge its secrets. The uncertainty of the smallest things paradox compels us to acknowledge that the micro-world is not governed by the deterministic laws of classical physics, but by probabilities and statistical behaviors that challenge our intuition. This uncertainty is not just a curiosity, it is a foundational element of the quantum world. It underlies phenomena like quantum tunneling, where particles pass through barriers that, by classical standards, should be insurmountable. Such effects have led to breakthroughs in technologies like semiconductor devices and quantum computing. Yet, the paradox remains. How do we reconcile a world where outcomes are fundamentally unpredictable with our need for certainty in everyday life? The principle implies that reality at its core is a landscape of possibilities rather than fixed states. The uncertainty of the smallest things invites you to imagine a universe where the act of observation itself creates reality, a cosmos where precise measurement is forever out of reach, and the beauty of nature lies in its perpetual mystery. Allow this thought to settle as you drift toward sleep, a reminder that even the tiniest particles exist in a realm where certainty is an illusion, and every moment is a dance of probabilities, shaping the very fabric of existence. Level 96. The equation that defines reality. Schrödinger's equation is often hailed as the cornerstone of quantum mechanics, a mathematical formula that predicts the behavior of particles at the quantum level. It describes how the wave function of a quantum system evolves over time, providing a probabilistic map of where particles might be and how they interact. But beyond its technical prowess, this equation invites us to ponder. Does it define reality itself? At first glance, Schrödinger's equation is a tool, a means to calculate probabilities in the quantum realm. Yet it suggests a universe where particles exist in multiple states simultaneously, and only upon observation do these possibilities collapse into a single, tangible outcome. In this view, reality is not a fixed structure but a dynamic process, continuously shaped by probabilities and observation. This paradox forces us to consider that the very act of measurement might play a role in creating the reality we experience. Some interpret the equation as indicating that the universe is inherently uncertain, a place where the future is a range of possibilities rather than a single predetermined path. The equation's predictive power lies not in certainties but in probabilities, challenging our classical ideas of determinism. Every time we observe a quantum system, we are effectively choosing one outcome from a myriad of possibilities, described by Schrödinger's equation. Moreover, if the equation governs the behavior of the microscopic world, can it also extend to the macroscopic? Some theories propose that the same principles might underpin larger systems, suggesting that the uncertainty and fluidity observed at the quantum level might, in some form, be present throughout the universe. In this light, Schrödinger's equation becomes more than a mathematical model. It becomes a window into the very nature of existence, hinting that reality itself is a tapestry woven from probabilities and potentials. As you settle into a peaceful state, consider that the equation might be the fundamental language of the cosmos, a code that, if deciphered fully, would reveal the hidden mechanisms behind every particle, every interaction, and every moment of existence. The equation that defines reality challenges us to see that our world, with all its apparent solidity and certainty, might actually be built on a foundation of subtle, probabilistic truths that continually shape our experience of reality. Level 97. The spooky connection across space. Imagine two particles, separated by vast cosmic distances, perhaps one on Earth and the other in a distant galaxy. Yet when one changes its state, the other responds instantly, as if connected by an invisible thread. This phenomenon, known as quantum entanglement, defies our classical intuition. In the quantum realm, particles can become entangled so that their properties are intrinsically linked, regardless of the space between them. When one particle is observed and its state determined, its partner immediately chooses a corresponding state. This spooky connection, as Einstein famously described it, challenges our understanding of causality and locality. Quantum entanglement suggests that information about one particle is somehow shared with its distant partner, even if they are light years apart. This instantaneous link appears to bypass the speed limit set by the speed of light, raising profound questions. How can two separate particles communicate without any signal traveling between them? Is our classical idea of space and time incomplete? Researchers have confirmed entanglement in countless experiments, demonstrating that nature at its most fundamental level is interconnected in ways we are only beginning to fathom. As you relax and let your mind wander, consider that this mysterious connection might hint at a deeper unity in the universe. Perhaps beneath the surface of our perceived separateness, everything is linked by hidden, instantaneous bonds. The spooky connection. Across space is more than a quantum oddity. It is a glimpse into the underlying fabric of reality, where distance becomes irrelevant and the universe is woven together by threads of entanglement that defy conventional understanding. Imagine the possibility that your thoughts, too, are connected in such a way. Across space, across time, a network of consciousness that mirrors the quantum world. This idea is both humbling and exhilarating, suggesting that the universe is a single vast entity where every part influences every other. In contemplating this mysterious connection, you might begin to see that the boundaries of space are not as rigid as they seem. The spooky link between entangled particles may be a reflection of a deeper truth, that everything in the cosmos is intertwined in an intricate dance of energy and information. As you drift towards sleep, let the thought of this invisible web of connections lull you into a state of wonder, where the universe reveals its hidden unity, whispering that no matter how far apart we are all part of the same cosmic fabric. Level 98. The Collapse of Possibilities. Imagine a world where every event, every decision, and every moment exists in a state of infinite potential. In the quantum realm, particles don't have fixed properties until they are observed. Instead, they exist in a superposition of all possible states at once. This mysterious condition is encapsulated in the concept of the collapse of possibilities, a phenomenon where, upon observation, a multitude of potential outcomes suddenly converges into one single reality. Before measurement, an atom is not located in one specific orbit, but is spread out across many possible orbits, each with a certain probability. It's as if the particle is everywhere and nowhere at once. When we measure the electron's position, however, the wave function collapses, and the electron is found at one particular location. This collapse is not a gradual process, but an instantaneous one, leaving us with the profound question: what triggers this sudden narrowing of possibilities? The collapse of possibilities. Paradox challenges our classical intuition that reality is predetermined. Instead, it suggests that the act of observation plays a crucial role in shaping the world around us. Every time you make a decision or observe an event, you participate in this cosmic act of collapsing a myriad of potential futures into one definite outcome. It is as if the universe is a vast field of probabilities, waiting to be shaped by your attention and perception. As you let your thoughts wander into sleep, consider that the uncertainty of life might be the source of its greatest beauty. In Ani, a world where every possibility exists, every moment is charged with potential energy. The collapse of the wave function is not merely a quirk of quantum mechanics. It may be the fundamental process by which reality is created, moment by moment, as countless possibilities converge into the singular narrative you experience. Allow this idea to settle in your mind, that your observations do more than record reality. They help create it, collapsing a spectrum of potential outcomes into one vivid, tangible moment. In this view, every decision, every fleeting glance carries the weight of infinite possibility, waiting to be transformed into the reality of your life. Level 99. The Secret of the Vacuum. When you picture empty space, you might imagine a void, a barren nothingness stretching out infinitely. However, modern physics tells a different story. The vacuum of space is anything but empty. Instead, it teems with ephemeral activity as particles continually appear and disappear in a phenomenon known as quantum fluctuations. This is the secret of the vacuum. A paradox that reveals emptiness is a misnomer for a vibrant, energetic background where virtual particles flicker in and out of existence. In quantum field theory, the vacuum is the lowest possible energy state, yet it is never truly at rest. Tiny bursts of energy spontaneously create particle-antiparticle pairs that exist for only a fleeting moment before annihilating each other. These virtual particles are not directly observable, but their effects can be felt. They contribute to forces such as the Casimir effect, where two uncharged metal plates placed very close together experience an attractive force due to the pressure difference created by these fluctuating particles. The secret of the vacuum challenges our intuitive notion that space is a passive, inert backdrop. Instead, it is an active, dynamic arena where energy and matter are in a constant state of flux. This hidden activity plays a crucial role in many phenomena, from the stability of atoms to the propagation of light and even the expansion of the universe. The idea that empty space contains a hidden wealth of energy opens up possibilities that stretch our imagination. Could we someday tap into this vacuum energy as a limitless power source? As you relax, allow your mind to contemplate that the nothingness between the stars is filled with subtle, ceaseless motion. Every moment, countless particles are born and vanish, contributing to an unseen symphony of creation and destruction that underpins all of existence. The vacuum is not void, but a fertile ground for quantum events, a mysterious, restless energy that reminds us that even the emptiest space is alive with possibility. Level 100. The theory that explains it all. For decades, scientists have sought a unifying theory, a single framework that can explain all fundamental forces and particles, from the smallest quarks to the vast expanse of the cosmos. The theory that explains it all is the ultimate quest in physics, a pursuit to stitch together the seemingly disparate laws of nature into one elegant tapestry. Our current understanding is built on pillars like quantum mechanics and general relativity, each remarkably successful in its own domain. Yet these two great theories remain incompatible in many ways. Quantum mechanics governs the behavior of particles at microscopic scales with inherent uncertainty and probability, while general relativity describes the smooth, continuous curvature of space-time in the presence of mass and energy. The challenge lies in reconciling these views into a single, cohesive theory, a theory of everything that unites all aspects of physics. The search for such a unifying theory has led to various proposals such as string theory and loop quantum gravity. String theory, for instance, posits that the fundamental constituents of reality are not point particles, but tiny, vibrating strings whose different modes of vibration produce the particles we observe. This elegant idea has the potential to explain gravity, electromagnetism, and the nuclear forces within a single framework. However, despite its mathematical beauty, string theory remains unproven and subject to intense debate. The theory that explains it all. Paradox challenges us to consider that the answer might be simpler than we think. Perhaps the key lies not in overly complex mathematical formulations, but in recognizing an underlying symmetry or principle that ties together all of nature's forces. What if the universe is built on a set of basic rules, so fundamental that they underpin every interaction, every particle, and every phenomenon, from the flicker of a distant star to the dance of subatomic particles? As you settle into sleep, allow your mind to wonder at the possibility that the secrets of the universe might be within reach. A single, elegant theory waiting to be discovered that unites the myriad mysteries of existence. The theory that explains it all invites you to journey into the unknown, where simplicity and beauty converge to reveal the hidden order behind the cosmic chaos.